За, усны шинжлэх ухаан ба инженерчлэл 2023 олон улсын хурлын маань 2 дугаар хэсэг эхлэх гэж байна. За, энэ хэсэг маань болохоор англи хэл дээр явагдана. Тэгээд та бүхэнд орчуулгын төхөөрөмж тараагдан. За, англиар сонсож байгаа хүмүүс бол орчуулгын төхөөрөмжгүйгээр шууд сонсоод явна. Good morning, good afternoon, good evening, where you are now. So we are going to start our international session of Hydroscience and Engineering 2023. So I would like to say some notes for this session, because this session will have synchronous translation, because many participants are from Mongolian. So you will find some instruction on chat section. So welcome everyone. So I'm very happy to open international session of this conference. So we had a Mongolian session this morning, and it was so tight, and this session will also be very tight because we have many presentations. And I would like to note that all presentations will have 20 minutes and 25 minutes for talk, and the rest of 5 minutes will be for question and answers. Can you hear me who are virtually joining with us? Professor Tom Sklarski, Professor John.
Yes, everything is fine. Thank you.
Okay, thank you. Thank you.
All okay for me too.
Oh, that's good. Thank you so much. So now, according to the program, we have opening session. So I would like to invite Dr. Otsuren, Scientific Secretary of Institute of Geography and Geology of Mongolian Academy of Science.
Dear ladies and gentlemen, so it's my pleasure to welcome you to the International Conference on the celebration of 16th anniversary of preparing hydraulic engineers in Mongolia. On behalf of organizing committee, I would like to express my gratitude to the presence of all delegates, speakers, and participants in the Hydroscience and Engineering 2023 International Conference. It's my honor to welcome our invited speakers and presenters for international session. I'm sure that Hydroscience and Engineering 2023 conference will achieve its objective as it provides an effective forum for academicians, researchers, and participants in advancing knowledge, research, and technology for community. It has been mentioned that the agenda of this conference covers a wide range of interesting topics related to theoretical and practical aspects, but not limited to hydroscience and engineering. I would like to thank you all presenters and participants who joined this conference via online from all over the world. I sincerely hope that through your presentation and discussion afterwards, all of us can contribute for solving water-related problems in our own countries. Even though the contribution may be small, but it is still valuable. Finally, my deepest gratitude goes to the organizing committee, institutions, companies, and volunteers who have directly and indirectly supported and sponsored the conference, especially the School of Civil Engineering and Architecture, Mongolian University of Sciences and Technology, and Water Division of Institute of Geography and Geology, Mongolian Academy of Sciences, and UNESCO Chair for Sustainable Groundwater Development Management. I wish you all the best for a successful conference and looking forward to future collaborations. Thank you very much.
Thank you, Dr. Otsuren. And I would like to invite Professor Solombatar, Director, Department of Research and Technology, Mongolian University of Science and Technology.
За сайн байцгаана. Өнөөдөр энэ танхимд ихэнх нь нөгөө Монгол улсууд байгаа болохоор англиар, монголоор тавханд директорийн өмнөөс одоо их сургуулийн мэндчлэгийг бас төвшүүлье. I would like to say the opening remark to Mongolian and English because so most of participants in here the Mongolians. Yes. Good afternoon, ladies, gentlemen, and distinguished guests. Өдрийн мэнд хүргье, эрхэм хүндэт ноёд татагтай нар төлөөлөгчдөө. I am very pleased to attend today's international conference on Hydroscience and Engineering 2023. За би энэ эрдэмчлэгээний хуралд оролцож байгаадаа маш их баяртай байна. Тэгээд эрдэмчлэгээний хурлын маань нэр одоо Усны шинжлэх ухаан ба инженерчлэл 2023 гэсэн эрдэм шинжилгээний хурал юм аа. Today we have celebrated the 60 years anniversary for establishment of the first department of hydro engineering in Mongolian University of Science and Technology. За өнөөдөр бид бүхэн шинжлэх ухааны технологийн сургуульд усны чиглэлээр дээд боловсролтой мэргэжилтэн бэлтгэсний 60 жилийн түүх тоог тэмдэглэн өнгөрүүлж байна. Congratulations to all faculty members and graduates who are joining us today. Ингээд 60 жилийнхаа түүх тоог тэмдэглэж байгаа эрхэм хүндэд одоо тэнхмийн профессор багш нар, ахмад профессорууд, нийт төгсөгчдөө баярын мэндчилгээ хүргье. Thank you very much to all who attend this conference, and special thanks to the participants from the Japan and Austria and Poland and Germany and India and Mongolia. За өнөөдрийн эрдэмчлэгээний хуралд оролцож байгаа нийт оролцогчид болон ялангуяа гадаад орноос Япон, Австри, Герман, Польш, Энэтхэг, Япон зэрэг орны эрдэмтэд оролцож байгаад онцгойлон талархаж байна. I would like to thank you very much to organizing committee on this conference and giving us good opportunity sharing our experience with university researchers and water and environmental engineering researchers. Өнөөдрийн эрдэмчлэгээний хурал маань бидэнд маш их одоо туршлага солилцох ялангуяа гадаадаас оролцож байгаа өргөцсөн илтгэгчд маань одоо энэ чиглэлээр усны шинжлэх ухааны чиглэлээр туршлага солилцох юм сайхан үйл ажиллагаа болж байгаад би их баяртай байна. Climate change and water resource and water quality are very important problem in the world. Цагуурын өөрчлөлт, за усны нөөц, усны хомсдол, усны менежментийн чиглэл асуудал болохоор дэлхийн нийтийн өмнө маш их тулгамж байгаа асуудал юм аа. Therefore, our invited speakers and presenters will talk about how to solve these challenges for exchange knowledge. За ийм ч учраас өнөөдөр оролцож байгаа илтгэгчид маань энэ чиглэлээр энэ асуудлыг яаж шийдэж байгаа тэрүүн туршлагаа бас солилцох юм сайхан бололцоог нээж өгч байна. So finally, I wish you success for all the participants in this conference. Thank you very much. За ингээд эцэст нь одоо нийт оролцогчид болон оролцогчдоо эрдэмчлэгээний хуралд нь амжилт хүсье. Баярлалаа.
Thank you very much, Professor Solomon Batar. So this conference, this international conference is co-organized by UNESCO Chair in Sustainable Groundwater Management. So I would like to invite Professor Maki Tsuchimura to make congratulations remark.
Thank you. It is great, honorable, and my pleasure to have a chance to show remarks on these important occasions. I would like to present my sincere congratulations, 60th anniversary of hydraulic engineering higher education in Mongolia, the commemorative international conference on the Hydroscience and Engineering 2023. I would like to have sincere respect to all participants in this important symposium and conferences on behalf of UNESCO Chair activities in Mongolia. UNESCO Chair on Sustainable Groundwater Management in Mongolia was launched in 2007 by the Chair, Professor Tanaka, University of Tsukuba, Japan, and Dr. Janchiv Doge, the Institute of Geography and Geoecology. Since then, we performed very important activities such as monitoring of the groundwater hydrological observations, capacity building, and construction data set, and construct basic for sustainable performance of UNESCO Chair's activities or performances. I believe the UNESCO Chair activities have great contributions to enhancement or promotions of knowledge and capacity buildings regarding the groundwater resources, which is one of the most important water resources in Mongolia. The water and groundwater are very important key issues in the global scales under the climate change conditions, especially in the semi-arid regions. So I believe that Mongolia civil engineering sectors would lead these topics in the world scale and global scales. And as the UNESCO chair activities, that would contribute and collaborate Mongolian sectors and communities regarding the water resources. And also I believe today's conference would great contributions to solve the water-related issues in the global scales. Finally, I would like to appreciate and show my sincere respect again to all organization committees in these important conferences. Thank you very much for your attention. By Allah.
Thank you, Professor Maki Tsuchimura. So thank you all guests who have made opening remark and congratulations remark. So I would like to draw your attention that this session is chaired by me, Ayurzan Badarch, from Mongolian University of Science and Technology. Also, Dr. Bolortsik, Officer of Program Cooperation Department of Institute of Geography and Geoecology of Mongolian Academy of Science. So I would like to invite Bolortsik to continue this session.
So good afternoon, everyone. I wanted to say thank you to Dr. Otsurung, Professor Salman Batar, Professor Maki Tsujimura for opening and congratulatory remarks. As we have on the agenda, the first part of this international session will begin with keynote presentations. And before I introduce our first keynote speaker, for all speakers and presenters, just to keep in mind that you have 20 minutes to present, but try to keep 2 to 3 minutes for the questions from the audience. So our first speaker, keynote speaker is Professor Hosoyamada Tokuza, who's head of Department of Civil and Environmental Engineering, Nagaoka University of Technology in Japan. So Professor Hosoyamada Tokuza will present on one-dimensional numerical analysis of tsunami and atmospheric sound waves caused by volcanic eruptions. Please welcome.
Okay, thank you, Chairperson. Can you hear my voice? Okay.
Yes, we can
Okay.
hear you clearly.
Okay, thank you. Thank you again. So I'd like to congratulate you on the 6th anniversary of founding Academy Society. My name is Hosoyamada Tokuzo, Professor of Civil, Chair of Civil Engineering Department in Nagaoka University of Technology, Japan. I'm honored to be invited as a guest keynote speaker this time. The title of my lecture is One-Dimensional Numerical Analysis of Tsunami and Atmospheric Sound Wave Caused by Volcanic Eruption. This is a topic of the tsunami generated from a submarine volcano that occurred in January 2022, that is about 1 year and 3 months ago. This topic doesn't have much to do with Mongolia because as you all know, Mongolia has no coastline. Japan, where I live, is surrounded by the sea, so half of the hydraulic problem are related to sea. So it's an unusual aspect to Mongolia, but I would be happy if I could draw your attention even a little. So prior to the lecture, instead of introducing myself, I'll talk about my relationship with Mongolia in 20 seconds. The university where I work and Mongolia University Technology, MUST, share an educational program called training program. So I managed it. The other is the research guidance of Dr. Arizana Badarch, faculty staff member of MUST. He's involved in this organization of this conference. Okay. Let's go back to the topic. On January 15/2022, a submarine volcano called Tonga Hunga Hapai erupted. I'd like to see some videos. This eruption was historically record scale, and the interest of experts gathered. In particular, Japan has suffered many damage from tsunami in the past. A tsunami disaster in 2022 killed more than 20,000 people. There is a lot of interest in tsunamis in the warning. So, sorry, this slide is too wordy. This time, a phenomenon called meteor tsunami occurred. Of public concern, the predicted arrival time was much later than actual arrival time of the tsunami. In addition, the volcanic eruptions caused atmospheric vibration, but there's a question, what exactly is meteor tsunami, which is largely unknown, right? In Japan, we have some similar phenomena called abiki, which is caused by atmospheric pressure difference observed on the western coast of Japan. the phenomenon of meteor tsunami caused by volcanic eruptions is a rare occurrence, and so social interest has increased. I've been interested in whether the observed water level fluctuation in meters could occur with the pressure difference of at most a few hectopascals, in fact, about 2 hectopascals. Also, the equation governing the phenomena should not to be difficult. So, incompressible fluid equation can be used for atmospheric pressure fluctuations, and sea surface wave corresponding to atmosphere fluctuation can be modeled as a storm surge system. It should be fine. So therefore, we built a model and try to easily confirm the phenomenon. So here we will study the basic property of meteor tsunami on paper. The figure will appear several times later. Since air vibration are sound wave, they propagate at speed of sound. Its speed is about 340 meters per second. So the horizontal axis of this diagram is horizontal direction. The vertical axis is elapsed time. The eruption wave generated at the origin propagate in the x direction according to time. So it goes from upper left to lower right, right? So the change in the front became these lines. Yeah, you can see blue and red lines. The faster the speed, the more horizontal the straight line. The speed of sound is in red and water waves are in blue. So the 3 graphs shown here are 3 patterns of relationship between speed of water waves and the speed of sound, depending on the water depth. So this schematic diagram is an image of water wave propagation when speed of sound and the wave speed are the same. The pressure difference occur in front of into front of and behind the wave front of the sound wave, and it spread out from a volcanic crater as a 3-dimensional spherical surface. The pressure difference caused by this sound wave is approximately 2 hectopascal. I will show you later. So the phenomenon may occur at a water depth is 12 kilometers. So this figure are spatial temporal diagram of water surface fluctuation caused by sound waves passing over sea surface with a uniform depth, and the distance is 500 kilometers. The 6 types of diagrams are different in water depth. So, when the water depth is 50,000 meters, the water surface velocity is faster than the sound wave. I think this slide is very complicated. Meteor tsunami is generated according to the propagation of sound waves, so it is useful to observe changes in waveforms seen from coordinate system that moves with sound. So this figure shows water surface fluctuation seen from coordinate system moving along the sound wave. Okay. So I created the pressure as a half wave of sinusoidal wave. Sound wave moves on the sea surface at the speed of sound, and the distribution of water surface wave seen from the front is shown in the lower graph. The red line is the latest or final state, and black line goes backwards in time every 147 seconds. It is plotted by comparing it at 5 different wave depths As you can see from these figures, the best case is the upper right, where the water depth is 12,000 meters. This one. So there are no occasion with such depths on Earth actually, because the deepest ocean on Earth is just under 11,000 meters. Oh, no. In case the sound and surface wave have the same velocity, and the surface can significantly amplify like this. And so next is this is the case for atmospheric pressure with skew symmetry, like this. Previous one is a sinusoidal one. Next is skew symmetric. The most important wave form is again this one, 12,000 meter depth, where we can see fairly large amplification of water surface waves. Finally, you can see that water surface has risen to 60 centimeters. So the water surface wave by meteor tsunami is related to wave velocity and the symmetry of the pressure waveform. And the figure on the right shows the comparison of the water levels rising at 5 kilometer point at the downstream end here. The horizontal axis indicates the ratio of wave velocity and sound velocity. It increased sharply at 1 here and decreased sharply after passing 1. The preliminary examination so far has been almost expected, and we have judged that it is fully satisfactory. And on the next slide, we'll try to apply it to the actual sea area. So let's see, apply the approach so far. So the volcanic eruption. Tonga is located here, and Japan is here. You can see that it is located directly across from Japan. The distance is approximately 90,000 kilometers. Yes, it will take about 7.4 hours at the speed of sound. We have actually calculated the tsunami and sound waves propagating this distance. So given the latitude and longitude of 2 points AB on Earth, shortest distance between the 2 points are great circle. So we need to find the latitude and longitude on the great circle. In this calculation, A is a volcanic crater and B is a Vladivostok, Russia. The great circle will pass through Tokyo. The number of division points, that is, say, the number of grids was set to 1,000. So this figure shows the actual calculated latitude and longitude grid point plotted on Google Earth. Although the yellow line looks straight, it is actually made up of 1,000 points. The point indicated by white arrows, and here are Tokyo, and Maizuru, Shishijima, and Amami Oshima. And so we have an observation data around this point, on this point. So for tsunami calculation, it is necessary to obtain water depths for all these 1,000 grid points. This time we interpreted the water depth and latitude and longitude of the grid point using E-top5 dataset. So this figure, so this black line shows the water depth along the yellow line, and from the crater, it gradually deepened to Japan, and there is a shallow sea area that seems to be a seamount around here. This seamount. The deepest point is located here. The depth is 8,000 meters. The red line shows the wave speed to sound ratio. The maximum value is 0.8 here, and the seamount area 0.4, 0.3. So the paper, the upper side, the upper side slide is an enlarged view of computational grid point of Google Earth. The 4 observation points is here. So this number, the start time of observed water surface fluctuation and actual arrival time of tsunami and predict time of Japan Meteorological Agency. And this is the time lag. So in case there is a time difference of 3 or 6, 2, this case is 2, almost 3 or 6 hours. This indicates that the alarm has been largely disabled. This was reported with great surprise. Japan is sensitive to tsunami warnings because of its past experience with disasters. And it can be concluded that the cause of difference is meteo tsunami. So this is the governing equation. Sound wave propagating in the atmosphere is compressed fluid. So, and these are basic equation. One is a equation of motion and continuity equation of compressible fluid and equation of state. So atmospheric pressure and water waves are calculated by coupling on the same time step on the numerical calculation program. The lower right figure is a computational domain by Google Earth, where the calculated line is dotted line, and the atmosphere above them is here, around here. So, but this is a very big problem. It is necessary to consider the setting boundary condition. It is impossible to at present to give condition for pressure fluctuation due to volcanic eruption. We have only information about the level of eruption. So in addition, this time the calculation is different from real field. So therefore, without being too strict, we recommend that the volcanic condition can be calibrated by giving atmospheric wind speed divergence. Usually divergence is 0 for compressed fluid, but this is compressed fluid, so this value is not 0. So we made this value here, give here for boundary condition for eruption. So this is atmospheric condition, the US standard atmosphere, the 60 meter. So this slide shows the example of the temporal evolution of calculated spatial distribution of atmospheric pressure fluctuation. So the atmospheric tsunami is generated at the front of this pressure fluctuation and propagate according to the local water depths. In addition, the water depths, wave of atmospheric pressure fluctuation propagation on the surface, on the sea surface is called ram wave. So this figure is a spatial temporal diagram of water surface fluctuation with pressure fluctuation. The uppermost line, the tsunami, that propagates with the atmospheric wave is called meteo tsunami. The wave caused by the pressure fluctuation are coming after another, after chasing from the rear or later behind the front. We can also see that tsunami generated in Tonga by the strong pressure fluctuation here. So this time difference is very shock to Japanese. So this is arrival time, and this is predicted time. So, but I think this, okay. This is a comparison of time series. So we compare the time series of atmospheric pressure and sea level fluctuation on Chichijima. The figure on left shows the time series of water surface fluctuation and pressure fluctuations obtained by the calculation. You can see water surface change corresponding to the atmospheric pressure change. So the right shows water surface and pressure fluctuation of Chichijima observation. The similar to the pressure fluctuation caused by eruption and its subsequent pressure are seen. the pressure difference is roughly consistent with calculation. The water surface fluctuation do not match very well, but calculation grid doesn't exactly match Chichima, and calculation point is 1 point on the open ocean. So I don't think this calculation result anything to be pessimistic about. So this is summary. So I should like to, this is summary. We believe that we are able to get the outline of this meteor tsunami from these simple one-dimensional and two-dimensional calculation results. In particular, we were able to confirm that possibility that pressure fluctuation of several hectopascal could develop into tsunami of several tens of centimeters or even meters. I think that coupled calculation of atmospheric pressure fluctuation and sea surface wave can also be satisfactory, but it is still unclear how to give condition for pressure fluctuation caused directly by volcanic eruption. So far, I have introduced only one of the phenomena that has recently become a hot topic in Japanese hydraulics. Thank you for attention.
Thank you, Professor Yamato Takuza. I'm afraid to say that we ran out of the time for the questions. So I would like to move to the next keynote presentation. So it will be given by Professor Colin Blanchard. He's going to present on eco-hydromorphological processes in rivers, linking science and engineering. Can you hear us, Professor Colin Blanchard? You are muted.
Yes, good afternoon. Can you hear me?
Yes.
Yes, but I don't know if I can share here. Ola.
You should be able to share your screen.
Yeah. Just a second, Zoom has a problem. So now it works, good. Can you see my screen?
Yes.
Perfect. So thank you very much. And first of all, congratulations with this commemoration. I'm very glad to have the opportunity to give a presentation here. I would like in particular to thank Dr. Ayur, who invited me. And it's true, Dr. Ayur, that I have a link to Mongolia because he came already twice for visits to Vienna, to Austria, and we have a very good joint research program. So thank you very much, Ayur. The title of my talk today is quite ambitious: Eco-hydromorphological processes in rivers, linking science and engineering. And in fact, I was not aware that my presentation was only 20 minutes. So I have made slides available that cover all aspects of this title. But in the 20 minutes of my talk today, I will focus on the flow processes, so the hydro part. And I will focus on the flow processes because that is the basis for all the rest on the morphological processes and the ecological processes. I will also focus on meandering rivers as a kind of example where you find these processes. And this is a picture of a small river in the center of Switzerland. It looks very artificial in morphology. So it's too beautifully meandering, too regular. And this is what happened after a flood in 1987. So there was huge erosion, huge damage to roads, to a railway, to houses. And that disaster was in fact the inspiration of my research activities on the topic. And the questions of relevance here were, what is the maximum erosion that you can have in such a case? What is the flow forcing on the banks? And how can you protect the banks? Of course, this is in a built environment. This is a time lapse from Ucayali River in Peru, in Amazonia. We have a river that is not confined, that is not fixed. And you see that this is a time lapse of 28 years. This river is wandering around in the floodplain. So you have exactly the same questions of engineering relevance, but in addition, you also want to know how the river morphology develops, how the river planform develops. This is important, for example, if you need to build a bridge over this river. So let's take a look of what happens in such a meandering river. This is a very, very simplified conceptual representation. And an important process that is known since the 19th century was already described by Bouzinesque, for example, or by Farge, is that you have secondary flow or spiral flow in a band that is indicated by this blue line here. And that is a kind of mixer. It redistributes everything. It redistributes the velocity. So you see that it's not even, it increases typically from the inside to the outside. That causes an uneven distribution of sediment transport capacity. This leads to a depth typically that increases from the inside to the outside. And because you have a higher velocity and a higher depth near the outer bank, you tend to have erosion of the bank. So all this is known. How is this accounted for in engineering? Well, quite often by empirical models that just make a relation between this maximum or this velocity excess or this depth excess or the flow forcing on the bank simply in relation to an indication of curvature. Or you can also do it by means of a process-based model that describes all these flow processes. But when I started my research on the topic, the empirical models and the process-based models were very inaccurate. So my objective was to improve them. And I think in my vision of my research methodology, the first thing I do is to go to the field and to observe what really happens in nature. How do these processes occur in nature? And what you see here are two configurations where we performed field measurements and where we measured in particular bathymetries and the flow field. And we did indeed observe the secondary flow. This was, of course, not a surprise, but we also observed other processes, complex flow patterns near the banks, zones of horizontal flow separation and flow recirculation, wooded rivers that influences the flow and the bathymetry, and vegetation on the riverbed that also influences the flow and the bathymetry. So a lot of complexity in a natural environment and a lot of interacting factors that complicate the interpretation. And that is why the next step in my research was to go to the lab. And here you see images of two flumes where we did research, one in Switzerland, one in the UK. And in the lab, the idea is to mimic what we have measured in the fields. But the advantage of the lab is that we can isolate processes. We don't have all the processes in the same time. We can isolate processes and investigate them under controlled conditions. And what you will see in the next slide are patterns of velocity in the cross-section in the middle of this flume, in the middle of the band. At the left side top here, you see the pattern of the velocity as it evolves around the band. And in this figure here, you see a cross-sectional pattern of vorticity. So you see very nicely the secondary flow cell, and you see other complex flow features near the banks. Now, the advantage of the lab is that you can change conditions easily. So you can change, for example, the discharge or the flow depth, or that amounts to a curvature ratio. You can change the roughness of the bank. You can change the inclination of the bank. You can also work with a mobile bed. So you can investigate the role of individual factors under controlled conditions. Of course, the lab still does not give you a complete spatial temporal description of the flow. So then the next step, we did numerical simulations. These are images of the lab flume at the left and a relatively small natural river at the right. And these are simulations with an eddy resolving model, so it directly resolves the turbulence. So we first validated the model by means of our experimental data, and then we have a very complete description of the flow for both cases. Now, if I come back to my original questions, we have done now field measurements, laboratory experiments, and numerical modeling. But what do we do with this, and how can we answer our initial questions that were engineering questions? So this was all science. This gives us a nice insight in the processes, but how can we link this now to engineering? So these, these very detailed simulations that you have seen, you can represent them graphically here. They resolve all details of the flow. They are called eddy resolving simulations, but they come at a very high computational cost. So they are not feasible in engineering practice. So this is science, I would say. In engineering practice, you need computationally less expensive models, and you can average in time to get rid of the turbulence. You have to model the turbulence, of course. You can also average over the flow depth, then you have a 2D model, or you can average over the entire cross-section, then you have a 1D model. And of course, by averaging, you lose information. So the computation becomes less expensive, but you lose information. In engineering, quite often we use depth averaged models or cross-sectionally averaged models. And they can, of course, not represent three-dimensional flow features such as this secondary flow. But in my previous slides, I have shown and claimed that the secondary flow is very important. So we cannot simply neglect it. And the idea is to account for it, to consider it in these models by means of what we can call a parameterization, or you could also call it a closure model for secondary flow. And that is what I will show you in the next slides, the development of such a closure model. First of all, what is the secondary flow and what does it cause? It's essentially due to the centrifugal force, which you see here at the left side. And this centrifugal force pushes the water outside. Because the water is pushed outside, you tend to have an inclination here of the water surface. So the water surface is higher at the right side, at the outside, and at the left side. That causes a pressure gradient inwards. And this outward centrifugal force and the pressure gradient are on the average in equilibrium, but not locally. And the local difference is that green part here, and that drives the secondary flow. This can be represented by a momentum balance. This is simply the momentum equation across the cross-section in transverse direction reduced to its three main terms. And if you insert a velocity profile, for example, a logarithmic one, you can solve this equation and you will find a secondary flow that grows linearly with an indication of how strong the curvature is. This is all known since the 1950s. But we also know that this is a very inaccurate model and that it strongly overestimates the importance of secondary flow. So my contribution here was to improve this model, and that was mainly by accounting for nonlinear interactions. Your velocity profile changes Because of that, the driver of the secondary flow changes. All this is known, but the challenge was to model that in a simple way. I will not go into detail how I did this, but the model I developed predicted this here, this red line, as evolution of the secondary flow instead of this black line that was the prediction of so-called linear models. So there is a huge difference. The question then is this new model better or not? And the only way to know it is to do experiments and to test it. And so we found out by experiments that this model represents pretty well the measurements, the behavior of secondary flow in laboratory flumes and also in natural rivers. This model has been implemented in 2D codes. This is, for example, an application of the software of Delft 3D software. Here, an eddy resolving simulation, here, the Reynolds average simulation, and here, the 2D model with my model for secondary flow. And you see that you lose details on the flow fields, but it is computationally much, much less expensive. And so this is a model that is then used in engineering. Now, in the end, we were not really interested in the secondary flow. We were interested in erosion in the meander band and in the flow forcing on the bank. So what we need to know, in fact, is not how strong the secondary flow is, but what is more important is how strong this velocity here is near the bank and how deep the scour is near the bank. And that is the next step. We first needed to model the secondary flow, and based on that, we can model this velocity excess and this maximum flow depth. And this can be done by a 1D model. How do you do this by a 1D model? So standard 1D models, they just give you one velocity in the cross-section and one flow depth in the cross-section. The extension is that you model the velocity distribution by a function with 1 degree of freedom. And the simplest one is just a straight line. And the degree of freedom is then the inclination of the straight line. This is called here this parameter alpha s. And you do the same for the bottom slope, function with 1 degree of freedom. And here I took a straight line, and the slope of the straight line is this parameter a. And then a 1D model consists in finding an equation that gives you this parameter alpha s. And I will show you briefly how this was done for the flow distribution. And all the information is in the Navier-Stokes equations because they describe the flow. So by inserting this profile function in the Navier-Stokes equations and by making some hypotheses and by doing a lot of manipulations, all this was transformed in an evolution equation for this parameter alpha s. So this is a 1D model. It's a differential equation of first order. And the distribution of the velocity gradient is driven by all these factors here. So you have, it looks complicated. It's a very long term here, 4 lines. But the nice thing is that every single line clearly represents a physical process. So the third line, for example, is the effect of the secondary flow. And what is very nice about such a 1D model is that it shows you very clearly the influence of different processes and also how strong these processes are, because that is quantified here by a non-dimensional number. You can see, for example, for the effect of secondary flow, this non-dimensional number shows you how important it is, and it shows you that in a very shallow river, secondary flow is not important at all for the flow distribution. In a narrow river, it will be important. It also shows you that it's more important in a smooth river than in a rough river. And I think I'm running out of time. So again, how good is this model? Well, you only know it when you validate it by means of data. And we have validated by means of data, comparison to data in laboratory flumes, in small natural rivers, and recently also in the middle reach of the Yangtze River. So we have covered a quite broad parameter range for the validation. In my slides that I have made available, there is also the equation for the bed morphology, which is based on a similar development. And this model for flow and morphology has also been used in practice in the framework of the remeandering, renaturalization of some rivers. I will come to my conclusions because I'm running out of time. In fact, the point I wanted to make with this is we are living in an era of big data, numerical simulations, and I see more and more of this very high resolution numerical simulations. The main thing I wanted to show you in this presentation is that when you have a good understanding of the physical processes, you can build models, 1D models, relatively simple models that are computationally much more convenient to use and that have the advantage that they provide a lot of understanding in the problem because they show you the influence of different physical processes and they show you also how important these processes are for given conditions because that is indicated by a number of non-dimensional parameters. So these very high resolution models are computationally expensive and they are a kind of black boxes. These very simple models, they are very transparent and they are computationally very cheap. So I think these simple models, they are not outdated at all, but they are very, very important for science and for engineering. And I've just shown you the example of the flow modeling, but you can see also the example of the morphology modeling and even a component of the ecological modeling in the presentation that I have made available. So with that, I want to conclude my talk. Thank you very much.
Thank you, Professor Karmgert, for the great talk. And I think we have a time for one question. If you have a question, just raise your hand and ask from the speaker. And that's all the presenters who are attending virtually. If you have a question, please ask from Professor Karmgert.
Thank you, Professor Kuhn. So it's Ayur. It seems there is, yeah, there is no question at the moment, but I would like to thank you for giving us a wonderful presentation. I don't have a question, but I have some idea that this kind of research is very important in Mongolia because we have some rivers that has been affected by mining and also some harmful land use. That rivers has already lost the natural meandering of the channel, and we have lots of work to make that river reach as like a natural channel and renaturalize the channel. So I think that is very interesting topic. The eco-hydromorphological process is quite new and it's quite complex to make complete research.
Thank you for these comments, Ayur. Well, I hope we can collaborate also on that topic then in the future. I would be very glad.
Thank you. Thank you very much. And
thank you.
I think we should move to next presentation. I would like to invite Professor John D. Penton, who will talk about some thoughts on research in hydraulics. And Professor John, could you share your screen? Or should I share your slides?
I think maybe you have to, Ayur. Yes. One moment.
Yes. So I'm going to see your slides from here. and you can say next when you are going to.
So,
Okay, you can go ahead, please.
so you've got my screen there, have you? Share. Can
Yes, I
people
think you also see it? Can you see your slides?
Yes, I can. Yes. And you can hear me.
Yes.
Okay. So I'd like to thank you very much for this opportunity and to congratulate you on the 60th anniversary of hydraulic engineering higher education in Mongolia. Now, we will see that we'll run through a few points here: an introduction, simplicity and smallness. This is very vague material that I'm talking about here, nothing like earlier. And a good statement that I put in my lecture notes when I was a very young student. There is nothing quite so practical as a good theory. Where information is sparse, use simple, approximate solutions, then followed by some thoughts on hydraulics, education, research, and practice. The problem of induction, we will describe that later, and the selection of research problems guided by practice. So the introduction, and here we have something that I thought was actually very nice. It is especially poignant for me to write in celebration of the 60th anniversary of hydraulic engineering higher education in Mongolia. This year happens also to be the 60th anniversary of my own hydraulic engineering education, beginning at a small country technical college in Australia. And so in 1963, I studied the subject Hydraulics 1, and I first became aware of my love for the subject. And water is wonderful. Water with a free surface is even more wonderful, and so is water with a movable boundary of soil particles. Just as wonderful is the nature of our subject itself, and we have a number of aspects of our subject. We can have simple and powerful theories, sometimes incorrect theories, fundamental theories, ad hoc theories, faddish theories, theories that are fashionable, field and laboratory measurements and control, sophisticated numerical methods, complicated and sometimes wrong numerical methods, complicated phenomena being described simply, and simple phenomena being described complicatedly, etc. And also, of course, there is our community of scholars and practitioners, which, like the subject of water itself, we are innately gentle. Its soft characteristics attract such people and in return lend something back to those who study and use it. Water is wonderful. So firstly, I want to talk about simplicity and smallness. And one advocate of simplicity and smallness was a medieval monk and philosopher, William of Ockham, who was in Britain, and he developed the principle known as Ockham's razor, meaning things should be shaved down. If something can be explained without a further assumption, there is no reason to include that. So any explanation should be in terms of the fewest factors or parameters. Then along came Isaac Newton, also British, and he wrote something that is actually not simple at all. He was trying to be simple, but he failed. And so in rather archaic English, truth is ever to be found in the simplicity and not in the multiplicity and confusion of things. And as I write here, Newton did not follow his own advice re simplicity in his writing at the time. The following is better by none other than Albert Einstein, who said it much simpler: make things as simple as possible, but not simpler. It's the English in that is not entirely perfect, but I hope we all get the message. He also said, if you can't explain it simply, you don't understand it well enough. There is one incidental comment by Richard Hamming, which is an opening statement in his famous book on numerical methods, and it's a very provocative statement. The purpose of computing is insight, not numbers. Well, a computer scientist might be able to say that, but as engineers, I don't think we can say that. So there are various aspects of simplicity. That little sign there, a mathematical symbol, means implies and is implied by. So simplicity and understanding go together. There is nothing quite like understanding: to learn, to recall, to create, and to simplify. Simplicity goes with visual perception and understanding. Many scientists and engineers are highly visual, and that often goes together with applied mathematics if it is simple enough. Simplicity, and this is an interesting one, implies an ease of disproof in the sense of the Austrian British philosopher Karl Popper. If something is simple, it is likely to be more correct because it has withstood attempts to disprove it. To disprove it might be easy, and if it can be disproved, it would be. Modeling. One should make the simplest possible model, and if it works, good, but if not, refine it and repeat if necessary. Simplicity and fewer data rather than more. Too little data leads to a simple model. Too much data often leads to complexity. Use a simple model so as not to have to fit all that data. And here is one where simplicity does not have an advantage. And I've shown it with the symbol shown in red, does not imply and is not implied by. Simplicity does not necessarily lead to publishing of research. A disadvantage of simplicity is that reviewers are pleased to discover something that they can understand, and then they criticize and reject it, whereas something complicated that is beyond their understanding is likely to be accepted. But simplicity does not necessarily imply correctness. And so we have the famous theory for flow over a sharp-crested weir. And it was this theory that caused me almost overnight to fall in love with hydraulics in 1963. What I didn't know at the time was it's nonsense. So here we have a weir, a two-dimensional weir. The conventional hydraulic assumption is that the pressure distribution is hydrostatic, shown by the red dotted line. The actual pressure distribution is shown by the blue dashed line. More importantly, when we come to calculating the velocity, we use Bernoulli's theorem to calculate the velocity down here, and then we calculate the flow by assuming that the velocity is horizontal. In fact, coming off the weir, the velocity is vertical. So the assumptions are quite wrong. However, we get this familiar and widely used formula for the discharge Q, that Q is that little formula well known to people who have done open channel hydraulics. But a better way of solving the problem is not to use a theory that's wrong, but to use dimensional analysis. And so here we consider a very different approach where we consider the variables of the problem for a deep and wide channel are the discharge per unit width Q, the head over the top H, and gravity, gravitational acceleration. 3 variables, 2 physical dimensions, 1 dimensionless quantity. And so this gives us our formula without any poor assumptions, such as we had when we applied hydraulics. And this has shown that the relationship must be like this, hence the practical success of the conventional but irrational hydraulic approach. It had to work, even if we did it very badly. There is nothing quite so practical as a good theory. And if we consider the gradually varied flow equation, and this is one of the most widely solved equations in river and canal hydraulics, especially performed by common hydraulic software such as HEC-RAS, which requires an inefficient numerical method as it does not recognize that the problem is a differential equation. And the equation describes the variation of depth along a stream. And so that's the equation as it's put in all textbooks, however, without the term in red. And the term in red is a non-prismatic contribution due to the stream cross-section changing. And so in 10 books on open channel hydraulics I have consulted, only 3 actually include that term. It's quite scandalous. If we use then the Manning formula, Gaukler-Manning formula for the head loss, we find here is now our differential equation where all the functional dependencies are shown that we need to know exactly what the cross-section of the stream is, how it varies along the stream. It is a data disaster. And so we need to know all the details of the underwater geometry to solve it. And usually, of course, we know the geometry of the stream poorly. The Talvik, the bottom of the stream, is poorly defined. And above all, the value of Manning's N is rarely known accurately. And it's my opinion that to put trust in most solutions is optimistic to foolhardy. And so I say worse than a data disaster, it's a disaster of human and scientific judgment. Many organizations require detailed solution of the gradually varied flow equation for approval of hydraulic works, believing that they're going to get an accurate calculation when the actual geometry is poorly known. Samuels, however, obtained a simple, approximate mathematical solution to the backwater problem, which is usually what numerical solutions of the gradually varied flow equation require. A structure imposes a certain level on the stream and when it needs to calculate how far upstream the disturbance extends. And he linearized the equation and he, beg your pardon, and he obtained this solution as a simple exponential decay. So from, say, a bridge pier upstream, the depth decays exponentially. Simple answer, little data required, provides the physical insight that the rate of exponential decay upstream is small for gentle sloping and deep streams and greater for steep and shallow ones. And so now we come to the important part here. One can imagine standing by a river, you as a young engineer, standing by a river, the slope of the surrounding country is about 10 to the -4. And I suppose I'm talking more Australian conditions than Austrian conditions here. The water depth is about 2 meters. A professional colleague from the local council, municipality asks, the new bridge will cause a level increase of 10 centimetres. How far upstream would the backwater extend? And so here we have the approximate answer in a minute without having to conduct a hydrographic survey or having to invent artificial topography or using a computer program. And now I'm afraid I'm going to have to ask you to close your eyes, and because I'm going to skip over several slides here that will be in the printed text. I want to come to the end. I've run out of time. I've run out of time quite substantially. It seemed like a good idea at the time. And so to the School of Civil Engineering and Architecture of the Mongolian University of Science and Technology and to hydraulic engineering in Mongolia, congratulations and very best wishes for the next 60 years. Thank you.
Thank you, Professor John. So we had a very quick presentation. We still have 3 minutes for discussion. If there is any question, please raise your hand. And the presenters, guest speakers who are virtually joining with us can also ask question. So it was very nice talk. Thank you, Professor John. So it was actually very informative and very good for young engineers here.
Thank you.
Joining us. Thank you. So if there is no question, so we would like to continue with next presentation. So I would like to invite Professor Tom Sklorsky, who will talk about advances in river ice modeling and applications. Professor Thomas, yes, please share your screen.
Thank you very much. I will share the screen right now.
Thank you.
I feel really honored to be the part of this anniversary. I feel also a little bit shy with this company and our other speakers who show wonderful approaches for the research and general insight for the hydraulics. So I try to not make it too much lower from the previous ones. And my topic will be mostly related to the part of the river hydraulics which relate to the code processes and ice modeling, especially mathematical modeling is close to myself. I'm the Faculty of Civil Environmental Engineering, Gdańsk University of Technology. So I'm referring to some application and let's say pictures from my country, from Poland. I hope you enjoy them. So starting from the general view for the ice research and engineering, which I am honored to be the chair of the ice committee in IHR. I would like to say that this subject is close to many areas for engineering, which are because of the effect of the ice for a number of issues. From this, I would like to mention specifically ice jamming and flood protection related to the jam processes, also ice damage and shoreline onshore facility, ice load on the structures, specifically bridges, piers, and other hydroengineering structures which are within the river, and very important subject, which is sediment transport problems as Professor Felton said, it's an issue for the movement of the water and particles. And here we have also solid on the surface, I mean, solid water in form of ice, which they both interact. So I somehow referred into that to the previous lecture for the ecohydrology and related to the stability of the banks. This is quite complex issue. However, yeah, let's follow. Another issue is the icebreakers and Arctic ship design, but I will not touch that. And a raising issue for the habitat improvement and river restoration in cold regions, when mostly it's related to ice interaction to the shore, to the riparian structures of or vegetation, as well as sediment transport related to the river and renaturization in the cold regions. Shortly talk about ice processes, because maybe somehow new for a number of participants. So we have a process of the ice formation in the cold region when water start to calm due to the natural thermal processes related to the meteorological and the sun to earth location, which bring calming of the water. And then we need to distinguish between calm water, which is stationary or slowly moving water, and turbulent flow. For the calm water, we have vertical stratification and density effect related to the affecting cooling the surface of the water, and then formation of the skim ice, border ice, and static cover to the surface, which usually comes quite quickly during the cold nights. Obviously, we don't have shortwave radiation, and if there is no clouds, then even the radiation will proceed faster. And I think most of us experience that freezing surface of the stationary water in their own experience. From the other side, if we have flowing water in the fast-flowing water bodies as rivers, then we have turbulent flow, and this will not allow vertical stratification. Instead, we have insufficient amount of radiation from the surface. We have cooling of the whole water body and formation of the ice crystals within the entire water body, forming fragile, suspended fragile, anchor ice, pancake ice, and as the final process of the ice formation, due to the buoyancy effect, this crystal will go to the surface, forming pancake ice and juxtaposed cover or freeze-up ice jam. Juxtaposed cover means more smooth. Just this flows or pancake ice will form the rather smooth surface, surface on the water surface. But if there is a freeze-up ice jam, it's more packed, like maybe on this picture from the Inner Mongolia, from China, Yellow River, when the ice is more packed and more chaotically forming jamming. This may bring some problems by the backwater effect and flooding in consequence, but it's more like the beginning of the ice season. Later, it will stay. Refer to the ice to the thermal condition, of course, in more cold winters, then we'll be staying for the whole winter season. In some countries, like European countries, sometimes the breakup occur in the mid-winter. So it not necessarily will be in the spring, sometimes also mid-winter, the breakup may occur. What is the breakup? Is the effect of the thermal condition, again, bringing either way stationary state, thermal breakup, and open water, very mild condition, which not bring any significant problem, or in case of rapid change of the water level, then will be forced breakup and formation of the breakup ice jam, which usually bring problems related to the either way jam, flooding, blockage of the intakes, navigation, or shoreline erosion, which are experienced mainly in the past and bring some issues related to the ice research and engineering solutions. So what is the ice jam formation? Typically is the thick toe supported by existing obstacle, which will be either way morphology obstacle or physical object like existing cover or bridge, piers, or any object which is within the channel, which form extensive toe and then is developed upstream, causing rising of the water level and possible flooding at the upstream. This scheme show more or less the condition, and then for the extensive toe, we have undercover increased velocity, which may bring erosion and scouring at the toe location, but also bring some condition for the upstream section, which is affected by the ice jam for either way accumulation or scouring of the sediment. Several information about mitigation methods. Of course, as the engineers, we need to be able to release these issues related to the ice problems and find some solution to mitigate the effect. And then will be either way non-structural, so-called artificial breakup methods, which are actual being proceed during the ice phenomena, or structural measures which prepare the condition, prepare the site for not causing significant effect of the ice processes. By non-structural, we can distinguish ice blasting, which is commonly used in the Chinese rivers and rivers which has problems for the access from the other side. In Europe, we also use this as the last solution if there is really risk for the structures, but usually due to the environmental issues are reduced to the minimum. Also, excavators, dredging machines, including these amphibious solutions commonly used in Canada. And what is most common in our country is the icebreakers, which are specially designed ships which allow for the breaking ice. I'm talking about inland water, obviously. And structural measures, which are the specially designed structure for controlling ice run, either way stopping it conditionally or unconditionally. So there could be ice control structure, pier type ice control structure, or booms, which is the floating structures, which stop the ice conditionally in its location, which are specially designed for that. All right, now I would talk about the mathematical modeling, which is indeed, as Professor Fulton said, simple in context, but somehow complicated when it comes to the details. So I would try to touch only the simple part, not because I cannot explain the details, maybe partly somehow also, but I know there is limited time, so I will just touch it slightly to make you more convinced what we're talking about by the mathematical model. This is the dinerized model, which was developed by my supervisor, Professor Hung-Tao Shen in Clarkson University in the United States, New York, United States. And this model is two-dimensional depth average model, which allow water hydraulics and ice dynamics to be modeled and predict ice site location and extension of the ice formation. Because we're talking about ice processes, this, as I said, it's quite complex due to the fact that there is many mutual relation between a number of parameters involved, number of conditions which cause this process to be which bring the process which affect the ice dynamics. We need to distinguish hydraulics, sediment transport, but also thermal processes. For the thermal processes, we need to include the effect of the meteorological condition by the heat flux from the surface and mass exchange between water and ice. So this is the full model involved here, and also simplified approach. For the river hydrodynamics, obviously we're solving continuity and momentum equation, which involved ice processes by the thickness, concentration, and seepage flow through the ice, as is shown on the scheme, because we also allow the seepage flow go through the ice mass. For the river ice dynamics, the approach is quite simple, because we assume the momentum of the acceleration of the movement of the ice is just related to the summation of forces. The problem is how to properly model the forces, which are internal resistance, wind drag, water drag, and gravitational force. And velocity of the ice is affected by those summation of those forces. So water drag is the effect of the movement of the water, how it will drag the ice parcels with the movement. So this is in relation to the second power of the velocity, and of course resistance between ice and water. So relation between ice velocity and water velocity. Wind drag, of course, affected to the second power of the wind velocity, and of course coefficient and other parameters. And gravitational force is affected by the slope of the water surface elevation. Since I have no much space, so I will just go quickly through the application, because I said to mention some application. I know there is some projects planned also in the Excellenga River in Mongolia. Sorry, so I will refer to recently designed and proposed project on the Vistula River in Poland, which I have checked in from this aspect of the sluicing of the ice and ice effect on the structures. So the project is planned on the Vistula River, lower Vistula River in Poland, due to the increased traffic requirement, electrical, and also to produce green power. Still consider this to be the green renewable energy source. So this is the outline of the project, is the low head dam with sluice, spillway, and power plant, as shown on the scheme. Number of location has been distinguished, and we finally come out with this, which is indicated as shell level 1 on this scheme. It's here, but maybe not very important. What is important, there are the targets for the modeling of the ice processes. There are these two distinguished: establishing frame for the ice sluicing operation, because ice need to be sluiced through this spillway during the breakup time, and also ice jamming operation on the reservoir. And another issue, which is more ecological issue, it was redeveloping of the artificial islands, which are planned to be built within the reservoir as so-called ecological compensation, because due to the rising of the water level in the reservoir, number of sites for the bird nesting and bird nesting mostly will be flooded. So there are a number of sites which considered to be artificial islands to form nesting habitats for the birds within the reservoir. Of course, the existing islands are natural islands, and we as the engineer are not responsible for them to be formed and reshaped by the natural condition of the river. But since they are constructed as the engineering side, we need to consider them to be protected or not being flushed away during the flooding. And what was more important from my perspective, by the ice impact on the shore of the island. Of course, the island must be accessible by the animals, so may need to have a slope of the beaches which are sandy. So they are quite challenging for the ice processes which form quite significant load on the shore. So without going into too much details, I just show the islands along the shore of the reservoir, the orange ones here, maybe I'm not sure if you can see my cursor here. So first, of course, there was the issue for the ice sluicing, which I mentioned as the first. So there was some section when the bridge was across the reservoir, there was need for analyzing this bridge pierce effect on the jamming, and then observation of the process by the ice modeling. What's the how extensive will be the jamming affected by the new reservoir and bridge piers, which are now under with the location of the water inundation place, and also this islands which are downstream of the reservoir and the shore of the islands will definitely bring some issues for the ice transport. So I indicate this, which need to be reshaped and remodeling for more smooth process of the ice run downstream of the reservoir. The flow direction is from the bottom to the up, and you can see this gray shape of the islands, which cause stoppage of the ice at the shore. With number of conditions has been tested, and just indicate that some of them need to be reshaped to not form too strong impact on the shore, which will bring definitely damage of the island. Some conclusion about ice modeling. Quite shortly, I would like to say that there are complicated processes because they're affecting numerous factors, including meteorology, hydrological condition, and also sediment transport. And all of that need to be considered. And what is more important, the ice load and ice effect on the structure cannot be ignored. Even though we're facing global warming, we can actually now say, because that's the fact that we observe warmer winters recently, but it does not bring the situation that we may completely forget about ice related problems, because this phenomena may occur. And since we are not used to every year mitigate the process, it may be even more challenging, less predictable. And at the very end, I would like to mention that we are planning the ICE conference, IHR conference in Poland. So whoever think that this subject is interesting, please come, please contact. We may like to invite you for being part of the conference. There will be many interesting keynotes, which will be shortly announced. And I'm very, again, thankful for having this opportunity to speak in this wonderful celebration of the 60th anniversary of the hydraulic engineering in Mongolia. Thank you very much.
Thank you, Professor Thomas. So it was quite nice presentation. At the end of the presentation, it was quite good to know that there is an ICE symposium is going to be held soon. So I think from Mongolia, there will be some participants at the conference. So we just run out.
Very good. I'm looking forward for that.
Yeah, thank you so much. Just we ran out our time. So it was on time actually. So I would like to move to next presentation. So our
According to the agenda, we have 2 more keynote presentations. There's a minor change in the agenda, so we're gonna have coffee break after the keynote presentation. So now I would like to introduce our next speaker, Dr. Sarah Mandel, a senior scientist at Ocean Engineering, CSIR National Institute of Oceanography in India. So he's going to present us about modeling the morphodynamics of a tidal dominated estuary. Please welcome.
Thank you very much. Also, thank you this organizing committee of Hydro 2023 team, especially Dr. Ayub for inviting me and giving me an opportunity for the keynote presentation. So I'll share my screen. This screen is visible.
We can see your screen.
Okay, so the topic is modeling the morphodynamics of a tidal dominated estuary. So basically, our institute in the west coast of India, where this monsoon is very high. So almost we received 4,000 millimeter of rainfall in a year. So in 3 months, almost 3 to 4 months, we received that kind of rainfall. And also there is no ice melting river in this coast. So most of the ice melting.
Mr. Sorry to interrupt you, but we can barely hear you. Can you speak closer to the microphone a little bit?
Yes. Now you can hear?
Yeah, it's much better now.
Yes.
Thank you.
Yes. So I am from CSIR National Institute of Oceanography. So this CSIR network has a 38 of laboratory all over India. So we do work on different research programs from climate change to coastal modeling. And also we involve in technology development from marine instrument to ocean engineering, wave energy devices, marine biotechnology, and also give service provided to the industry. So our office, our institute in Goa, which is in the mid central west coast of India. So when we go for the morphological modeling of a tidal dominated estuary, so first thing comes to us that how much the tidal flow goes inside that estuary, or goes how much deep inside the estuary. So we can do the modeling accordingly. So with that in mind, so we developed, we worked on in a method. So that will show by analyzing the water stage component of estuary at different location, the tidal influence. And if the tidal influence is good enough, so then that area we can do the modeling with the tidal boundary condition. Otherwise, we have to give the what is the influx from the upstream. Those boundary conditions we have to use. So it is important and essential to demarcate the estuary where the tidal flow is dominated. So these are the objective that first we determine the estuary boundary under the tidal influence. Then we used inside that domain the hydrodynamics and morphodynamics using a process-based numerical model, DEL 3D, under defined scenario. And then the model result will validate with our field measurement, and we draw conclusion from it. So for this morphological modeling, we conducted several field measurements. So first of all, as you know, we want to have the bathymetry of the model domain in which the estuary we are modeling. Then also we have to do that river discharge measurement. So generally we do the river discharge measurement with the ATCP. And then also at defined location, we have to measure the water level. So we can use the tide gauge or other method like camera. For that, we have to measure the water level. And then we require the current. Generally, if we want to have a single point current, so we use a recording current meter and we deploy at mid water depth. So in the video, you can see how the current meter is deploying from the boat, and it will be placed at the mid water depth. So then also we collect the suspended sediment concentration. So we collect at a defined depth, generally 3 depth, depending on how much deep the river. So we collect the water sample from defined depth at defined location, and then we process this water sample in the lab and find the suspended solids, so which is coming from the boundary. And then also we collect the bed sediment. Generally with the graph, we collect the bed sediment. So from that one, we can calculate what is the mean diameter of the sediment at different locations. So we have a spatially varied sediment diameter along that estuary. So with all this data, we can start the modeling. So before I told you that we need to first go into the modeling, we need to select the estuary boundary where it can divide the freshwater and saline water. So as the West Coast, we don't have much fresh water other than monsoon season, the 3 months. So there is, when we do the modeling, there is 2 parts we can divide. One is the non-monsoon time and one is the monsoon time. Non-monsoon time, mostly it is dependent on the tidal flow, which is you can predict actually. But the monsoon one, you cannot predict. So you have to do a heavy measurement during the monsoon, and non-monsoon time, without much measurement, you can carry out the model. So this slide, here the process to determine the estuary boundary. So now we have collected here you can see there is a defined locations is there. So this is one of the major estuary region, and here you can see there is a number of locations where we collected the major water level data. Now these water level data are the mixed. So with the because this is pre-monsoon and post-monsoon data was there, so just rainy season completed, so it was the mixed data. But we removed the residual, and then we analyzed that how much the influence of tide going inside. So then we break this tidal data, this tidal time series, into different parts by the water stretch components to understand the local tidal characteristic. So we used one method, CMMD. So that is what it does. It also with the Fourier analysis we can do that, but we have used Hilbert-Horn transform method to break this tidal data into different time series with different frequency. Now, how we have done that? we generally, it is done from the calculating, we find the local mean, as it is iterative process at a different time step. Sorry, not different time step. It is we calculated local mean and we add weighted value noise in that local mean, and we process iterative method. This process is called as this is by adding this this adaptive noise. This is called CMMD method, and by that one we break this tidal time series in different characteristics as a frequency, and then we use Hilbert transformation, and then after using the Hilbert transformation, we can get the local tidal characteristic. So this is the slide. So here in the left-hand side, you can see the first is the time series of the tidal, and after that, this tidal time series is break it into different parts, and you can see this is the most dominant tidal constraint, and this is the second most dominant tidal constraint. In the here you can see in the right hand side bottom, you can see this is the most dominant component, and these are the period of this tidal constant. So you can see that mostly the tide comes, it is cycle power hour. So tide comes 2 times at 12 generally 12-hour gap tides comes, and there's another signal is around 24-hour gap. So then we check how much this tidal strength at different location to check the strength. If these strengths are good, that means those areas are more dominated by tidal. So here I presented this graph for one location, and here in this figure, you can see here in the top figure is the wavelet transformation, and down is the Hilbert transformation. So this Hilbert transformation will give the more resolution in time. So here you can see this the signal around 0.08 hertz is very much strong, and at each time you can see the resolution is very good, but wavelet we cannot get that much of resolution. So this Hilbert transformation is much superior than wavelet for analyzing this kind of tidal data. So here you can plot it, and different places we have collected this water level data to check the tidal strength. So on the right hand side, you can see this M1, M2, M3 is this river, and where Z1, Z2, this river in this location, and where S1, S2 is the open ocean tide. So from this kind of graph, you can easily see this M1, M2, M3, this location are mostly not dominated by the open ocean tide. But in this second river, this Juari river, these are mostly dominated by the open ocean tide. And also the connecting channel between this Juari river and Mandovi river, this connecting channel location is mostly influenced by the tide of the Mandovi river. Whereas this location is very near to Juari river, but it is mostly dominated by tidal river. So the point is that with this kind of time series analysis, we can come to know that from where the water influx is coming, accordingly we can plan our groundwater recharge, any water resource management. If we can do the same analysis for the freshwater analysis and different portion, and how the salt intrusion happen. So all this analysis we can do by analyzing the tidal state. So with this analysis, we can demarcate, okay, this much tide can go strongly, and then we can choose our domain. So if the domain within this strong tidal range, so we can do the morphological modeling according to the boundary condition, which I'm going to describe next. So we conducted one numerical modeling where we use the DL3D modeling, process-based modeling, and we conducted hydrodynamics and morphological impact. So that river is impacting high bank erosion, and also in the monsoon time, very high river flow happening. Is around 2.5 meter per second during the monsoon, but in the non-monsoon time, almost 0.3 meter per second flow velocity. So this model is carried out in a 2D, not 3D model. So here the analysis is done on the depth average velocity. So there is a two case scenario is conducted. One is with the original bathymetry, which the river we have collected the bathymetry, and the second case we deep some location, we have dredged some location around 3 meter to show that how the bed level changes happen. For example, if someone doing this river mining or this kind of operations, so for environmental impact or morphodynamical impact, we need to know how the bed level changes if this kind of scenario happens. To look into that issue, so this kind of scenario has been created artificially. Then this first we did the hydrodynamic model, and then based on hydrodynamic model, the morphological simulation is being carried out. Now this hydrodynamic model, as I told before, there is a two season it has been break out. One is the monsoon season and one is the non-monsoon season. So generally in the monsoon season, what is the important thing is that what is the boundary condition we are taking. Now during the high water flow, we need to measure the water level at the both boundaries, and then we need to feed in the model, and then we have to measure current and water level at some portion of the river, strategic portion, and then with that one we need to calibrate the model, and in that way the roughness is adjusted. So we have not measured the roughness in the river, but this way we have calibrated the model for the monsoon. And we follow the same procedure during the non-monsoon time, where this high water, there is no water flow on the upstream, wherever the water is going from the ocean side, and that goes to up to certain limit, then coming back. So this is very regular thing in the non-monsoon time. So only the tidal boundary condition is the important, and it has been incorporated in the model. So with this thing, so this is the current validation during non-monsoon. So you can see the measurement with this knowledge, this measurement is quite good. Although definitely in the field measurement, in the river field measurement, the matching is not 100%, but it is well. During non-monsoon time, you can see the current E component and B component is quite high, but also the model can simulate with some expected output, and it is also patterned this way. Then all these dredged channel where this bathymetry was modified, there you can see this is the case 2 where the dredging happened, and so there you can see that due to the increase of the bathymetry water depth, the current speed becoming less. So, and the second option, second figure, you can see how the tidal current varies, and this simulation is carried out for the whole 8 months, where the 4 months is for the monsoon period. So non-monsoon period, it is mostly the tidal dominant. And here the monsoon time, you can see how the morphological bed level changes happen. Mostly 0.5 meter to 0.5 meter, the erosion blue is the ocean. You can see the upstream of the river is impacting high erosion because of the small wide and high current flow during the monsoon time. But where the dredging happened due to the slow, the deposition started there. But also, since the deposition started there, the other portion also getting the less suspended sediment. So this is a cumulative effect. So if we this river is dredged haphazardly, so there will be a high impact on the river, and the bank erosion will definitely happen. The river will lose the stability. So my previous speakers also has been talk about it in very detail. So non-monsoon time, we can see the mouth of the estuary mostly having the sedimentation, but in between the upstream of the estuary not having much sedimentation. So because the water is blocked and all the sediment, because no water is coming from the upstream, no fresh water, not added water, whatever water is going on from the downstream, because the downstream from the ocean side. So during non-monsoon time, the bed level changes is 0.1 meter to 1 meter. So almost, so here we can not do so much of mining, maybe 20 centimeter to 20 centimeter mining can be done in selected locations. So that is also, we need to see the other impact also, where is the biological any sensitive zone is there or not. So all these things we look into this, and accordingly we have to do for this sustainable engineering. So in this, I draw conclusion that we have demarcated first with the Hilbert-Simedal method for water stage component analysis. And this method is very effective for understand local tidal characteristic. And this boundary level data is one of the most important things for this process-based model. And also this hydrodynamic model is well agreed with our calibration. Then this non-monsoon time, since there is no fresh water coming from the upstream, so we can use the morphological factor so to save the time. So if we use we want to simulate for 1 year morphological changes, so with 1 month simulation, so we can give 9 or 10 and 9 morphological factors, so we can simulate for the whole year. So during monsoon time, the sediment transport happened mostly from the upstream to downstream, and the deposition happened at the downstream. Then during non-monsoon time, the tidal flow, then again it goes from the downstream to upstream. It start to push. So thank you, and also congratulations on the occasion of 60 years of hydraulic engineering and higher education.
Thank you, Dr. Saramato, for the interesting talk. Unfortunately, we don't have a time for the questions. So we are going to move to the next and the final talk. The keynote presenter, the final keynote presenter is Dr. Sarantoya Zandara. She's going to present us on science for water and sustainable development. UNESCO's action for a water secure world in a changing environment.
Сайн байцгаана уу? Энэ хуралд оролцож байгаа олон улсын болон Монголын эрдэмтэд багш оюутан залуучуудад энэ өдрийн мэндийг хүргэе. Мөн Монгол улсад усны инженерийн боловсрол байгууллага хэсгийн 60 жилийн өмнө барийн мэндийг хүргье. Намайг сонсож байна уу?
Сонсож байна.
Okay, yeah. So I'll now switch into English. First of all, it's my great pleasure to be invited to this 60th anniversary commemorative international conference on the hydroscience and engineering at the University of Science and Technology of Mongolia. And I'm very pleased to say that it is my home university. I graduated from the University of Science and Technology many years ago, and also this university is where I started my professional career as a professor, chair professor on environmental engineering, and also as the director of the Department of Water Resources and Environmental Engineering. So now I work at the Division of Water Sciences, which is the Secretariat of the Intergovernmental Hydrological Program of UNESCO based in Paris. And I will make a presentation on how UNESCO supports its member states in addressing water issues and also pursuing sustainable development through science, research, knowledge, and capacity building. Today, the world is facing serious global water challenges. One in every 3 person lacks access to safely managed drinking water, including over 1.2 billion people who lack access to basic drinking water services. And also almost the same people, 2 billion people lack access to basic sanitation. The water pollution in the different regions of the world is worsening with eutrophication, nutrient enrichment, mainly due to the discharge of untreated sewage or agricultural runoff. There are also new water challenges, such as the presence of new pollutants, which are called emerging pollutants, or plastic and microplastic pollution in freshwater resources. Food security is at risk due to water scarcity, while water for growing more food for the growing world's population is increasing. At the same time, also the countries as well as cities are facing water-related disasters, which are increasing in both intensity and frequency due to climate change. And we also have to keep in mind that over 90% of natural disasters are related to water, mainly floods and drought. The future scenarios for the water resources at the global level and the climate change impact predict or estimate that there will be significant future reductions in renewable water resources at the global level, which will affect the quantity, quality, and reliability of water resources. This will aggravate and exacerbate competing water uses between different sectors, such as cities, drinking water, or water for irrigation and agriculture, water for energy production, and water for industries and mining, at all levels, from local, regional to global levels, which may potentially lead to conflicts between different users. So water is one of the most crucial aspects of sustainable development, and water is at the core of the sustainable development. And we know that the UN 2030 agenda on sustainable development includes a standalone specific target on clean water and sanitation for all, the SDG 6. But also we have to highlight that the water is the key element for achieving all other sustainable development goals. In that regard, we can say that water cuts across all SDGs, all other 16 SDGs, because the SDGs include 17 goals. For example, water is essential for poverty reduction, which is the goal number 1. Water is essential for food production, which is goal number 2. Water is essential for human health and well-being, which is the goal number 3. And also water is vital for ecosystems and biodiversity, which is the goal number 15. And the sustainable management of water in cities is key to the adaptation and resilience of human settlements to climate change, which are goal number 13 on climate action and 11 on sustainable cities and communities. So we can actually find interlinkages of water with all sustainable development goals. So in that context, water is prerequisite for achieving other global agendas, such as the New Urban Agenda under the UN Habitat, or the Sendai Framework for Disaster Risk Reduction, or the Paris Climate Agreement of the UNFCCC Convention on Climate Change. So now I would like to give you some examples of how UNESCO supports its member states through science for a water secure world. So I will talk about some activities about the Intergovernmental Hydrological Program of UNESCO, which is called IHP. Many of you may have already heard about UNESCO's Intergovernmental Hydrological Program, and also I saw in the program that some of the participants are also part of the UNESCO's water program, such as UNESCO Water Chairs. So the IHP was established in 1975 after the International Hydrological Decade, which ran from 1965 to 74. So the Intergovernmental Hydrological Program of UNESCO is the only intergovernmental scientific cooperation program dedicated to water within the UN system. So our main goal is to promote research, to promote water education and capacity building in order to underpin sustainable management of water resources in member states of UNESCO. So our program is, because it's an intergovernmental program, our program is governed by the Intergovernmental Council and Bureau, which are represented by 36 member states elected through the UNESCO General Conference, representing 6 regions. And Mongolia was part of the Intergovernmental Council of IHP, I think, in 2010. From 2010 to 2014, I think. So here about the history and evaluation of the Intergovernmental Hydrological Program. Well, it started as a program, scientific cooperative program, purely dedicating to hydrology when it was established in 1975, but then the second and third phases of IHP expanded to water resources management. And then towards the 6th and 7th phases of IHP, the program also evolved into a holistic transdisciplinary program, including societal aspects of water management. And the now in the 8th or the 9th phase, program is further evolving into a holistic transdisciplinary program aimed to promote science for a water secure world in a changing environment. So you see that our program has really evolved as the global water challenges have also evolved throughout this past 50, 60 years. So now we are in the 9th phase of the Intergovernmental Hydrological Program of UNESCO, which is dedicated to the overall theme of science for water secure world. And our vision is to support the institutions, the countries, and also as well as build human capacity to help countries develop sound policies, management practices based on the best available knowledge, research findings, and innovative tools. So IHP, we don't do research at UNESCO, but we promote research which help shape research agendas and priorities, and we also disseminate the available scientific knowledge and make the available scientific knowledge as to policymakers to promote science-based policy development in order to attain sustainable development and build resilient societies. So the current phase, the 9th phase, focuses on 5 priority areas on research and innovation. So we promote scientific research and innovation so that the world scientific community, professors like yourselves, will address global water challenges. We also promote water education, take into account the evolving industrial advancements such as the artificial intelligence. We also help bridge the data and knowledge gap And also one of the priority areas is the integrated water resource management under conditions of global change, global changes including urbanization, population growth, and climate change. And the priority area 5 focuses on water governance based on science for mitigation, adaptation, and resilience. So there are 34 outputs and 150 key activities under these 5 priority areas. So here are some examples of specific water-related issues addressed under each of these 5 priority areas. For example, we promote research and innovation to address urban and rural water management or water-related disasters or water quality and pollution, sustainable groundwater management, or impact of global and climate changes on water resources. The priority area 2 focuses on water education, how to enhance and strengthen water-related curricula in formal and informal education at all levels, from primary to higher education, as well as how to promote water education as a part of lifelong education programs. In terms of bridging the data knowledge gap, there are programs focusing on the innovative water monitoring tools such as the Earth observation or artificial intelligence, big data, etc. And also one of the most important aspects is to promote open science and open access to data, which is critical for sharing scientific results and data with the world community across different regions and in different countries. The integrated water resource management priority area also promotes new and innovative approaches, such as reconciling or a holistic approach between upstream and downstream issues. The other key element is the incorporation of ecosystem services and environmental flows as part of water resource management. Another new approach is nature-based solutions to water issues. For example, nature not only provides water, but also provides very important ecosystem services such as water purification, protection of source waters, or nature-based flood management and protection. There are also new approaches such as source-to-sea management or source-to coastal area management, but Mongolia is a landlocked country, so we may not be talking about seas in Mongolia. But another key element is the nexus approach, for example, the water, food, and energy nexus. And last but not least, we promote science-based water governance. So all these activities and key priority areas are implemented through thematic working groups dedicated to these 5 thematic areas, priority areas. As well as there are 3 cross-sectoral groups focusing on hydrological systems, climate risk, and nexus. The second cross-sectoral group is groundwater management and human settlements, and the third is eco-hydrology and water quality. And we design, together with member states, activities to be implemented under these thematic working groups, as well as cross-sectoral groups. So UNESCO, so IHP program is not only the Secretariat or Division of Water Sciences, where I am based here, but we include a huge global network of stakeholders working with UNESCO on advancing UNESCO's objectives on water. So it is an intergovernmental program. We have national committees in almost all countries. UNESCO currently has over 193 members, in which we have IHP national committees in about 169 countries. And Mongolia also has IHP National Committee. And before joining UNESCO, I was part of the IHP National Committee of Mongolia. Another strong implementation partner of UNESCO's activities and projects on water is a network of UNESCO water-related Category 2 centers. There are currently 36 in all over the world, and we have over 70 UNESCO water chairs dedicated to water. And in Mongolia, we have one water chair hosted at the Geoecology Institute of the Academy of Sciences, co-hosted by the University of Tsukuba. Professor Chuzumura is present in this conference. And then UNESCO also hosts the World Water Assessment Program, WAP, which produces annual World Water Development reports dedicated to specific water topics. So with this global network, UNESCO aims to advance hydrological and water science knowledge to support sustainable water management. In addition, also, IHP has flagship initiatives dedicated to specific water issues. And I'm very pleased to say that the International Initiative on Water Quality was launched as a result of my activities and activities I implement. But there are also some, you see on this slide, that many initiatives that might be of interest to Mongolia. Now, I would like to give some examples of how we support addressing specific water-related issues. And these examples will focus on water quality and urban water. These are the themes that I lead in the Division of Water Sciences. So with regards to water quality, one of the key issues where the science can play an important role in addressing the water problem is emerging pollutants and microplastics in fresh water. So emerging pollutants are new type of pollutants that are naturally occurring or that have been discharged with wastewater or other waste into water resources. And we call them new or emerging pollutants because they are not monitored as part of routine water monitoring programs. And also these pollutants are not regulated in the environment or in water resource management. And these pollutants, new pollutants, have potentially known or suspected negative impacts on human health and ecosystems. There is very limited scientific understanding about the presence, occurrences, fate, and dynamics of these new pollutants in the aquatic environment. And there is also lack of regulation policies to manage emerging pollutants. So there is really important role to promote science, to develop appropriate policies and solutions to address these pollutants. And one of the key types of pollutants include pharmaceuticals for human use and veterinary use, as well plastics or microplastics. And we know that plastics have become an integral part of all the spheres of economic activities in our societies. But the negative result is that plastic waste and microplastic waste is a big problem in the environment. And actually, this is one of the triple environmental crises at the global level, together with biodiversity loss and climate change. So UNESCO implemented a project on emerging pollutants. And we implemented 16 case studies in over 20 countries. And here you see some of the results of the case studies published by UNESCO. I'm not going to go into details because of the time constraint for this presentation. We also disseminate the findings of research by the world scientific community. And recently, in January this year, UNESCO organized a major international conference on emerging pollutants, protecting water quality for the health of people and environment, which brought together over 160 research presentations from all over the world, as well as 2 high-level science policy panels with the participation of UN organizations and key academic institutions such as the Academy of Sciences of China or Water Research Council of South Africa. And the conference was attended by over 2,900 people worldwide. UNESCO also was part of the major European project on plastics in freshwater. And UNESCO hosted the final conference of the project, which disseminated research on addressing freshwater microplastic pollution from source to these impacts and solutions and the societies role. So this conference provided a platform for the dissemination of new knowledge, as well as research findings in order to promote science-based solutions for reducing microplastic pollution in water. Another example is innovative water monitoring from space via satellite Earth observation and UNESCO World Water Quality Portal. So in 2015, UNESCO implemented a demonstration project with the aim to demonstrate the potential of satellite Earth observation for water quality monitoring in inland fresh water resources, and how to promote such an innovative approach in order to support science-based policy making. And so here you see some of the demonstration basins, for example, Mekong River Delta, or a lake in Florida, this Nile River basin in Africa, and I think this is Rio in Latin America. So following the successful demonstration phase, UNESCO further developed this portal into operational applications, and the portal, UNESCO portal, has been applied for operational water quality monitoring in two big transboundary basins, Lake Chad Basin in Africa, shared by 5 African countries. And we are supporting the technical and human capacities of Lake Chad Basin Commission, and we developed a dedicated UNESCO World Water Quality Portal for Lake Chad, and we are doing the same for the operational water quality monitoring in a La Plata Basin in Latin America, again shared by 5 Latin American countries, and we are supporting, we are building this portal. We already have built for a pilot zone of the basin, and for these portals will be run and owned and transferred to these basin commissions of these river basins. Actually, UNESCO is just supporting these basin organizations to use these innovative approaches. So here, this portal provides almost real-time water quality data on the key water quality parameters using satellite images, and we developed this portal in cooperation with the French Space Agency and French research institutions. And the water quality data are available on these parameters such as turbidity, suspended solids, dissolved organic matter, or chlorophyll, harmful algal blooms, water temperature, as well as we also can obtain data on water surface area and water altimeter. The data are available on an open access basis and are provided in different formats, such as the time series. Also, the data can be downloaded in an Excel format to support the research, or data can be available as water quality maps, and this is actually the format which is preferred by users such as stakeholders or policymakers, because the information is available in a format that is accessible visually.
Dr. Sarantia, sorry to interrupt you. We already ran out of the time.
Yes, so do you want me to stop or I continue?
Go ahead, yeah.
Yeah. So then these data are validated by field measurements, as you can see, and UNESCO also provided this modern water quality measurement equipment probe to Lake Chad Basin Commission. So this is water quality surface area maps. So just very quickly in 2 minutes about the UNESCO's initiatives on water in cities and how to enhance water security in human settlements. So one of the projects that we're implementing is the City Blueprint Framework, which is a diagnosis tool to help cities assess which elements of the water management in cities need to be improved, which are sustainable, and we're currently implementing it in African cities. Another example is Megacities Alliance for Water and Climate, and focusing on cities with a population of 10 million and more. This is to provide a platform for cooperation among cities to help megacities adapt to and mitigate effects of climate change. And another project which might be of particular interest to Mongolia is the extra budgetary project on water security and human settlements under climate change. And through this project, UNESCO supports 10 countries in Africa and 10 countries in Asia in improving water security and human settlements in the face of climate change. So with this, I would like to end my presentation and thank you very much, and congratulations again on the 60th anniversary of the hydrological research in Mongolia. Over to you. Thank you.
Thank you, Dr. Sarantoya. So thank you very much for all our invited speakers. Now, unfortunately, we have no time for discussions for all our invited speakers. So thank you very much. And we will have now 10 minutes of break, and then we'll continue the next part of our session. So see you soon. За 10 минутын завсралгаа аваад тэгээд үргэлжлүүлье.
So let's get started the final session of the international conference. We have 4 presenters for this session. Please allow me to introduce first presenter, Professor Maki Tsujimura. Title of his talk is Tool River and Groundwater Interaction in Ulaanbaatar, Mongolia. So please go ahead and share your screen, Professor Tsujimura.
Okay, thank you. Is it okay? Okay, now shall we start? So I would like to talk on river and groundwater interaction based on the findings or outcomes of the UNESCO chair activity in Mongolia regarding the groundwater management. As you may know, the groundwater is the most largest water body in a liquid phase and fresh waters all over the world. And more than 50% of the world populations depends on the groundwater as daily water resources. Therefore, we need to know about the basic dynamics of the groundwater's resources, especially in semi-arid and arid regions. However, there were not enough information regarding the groundwater recharge, especially in the semi-arid regions. Scanlon et al. Reported the previous researches on groundwater recharge, especially in the semi-arid regions. In the Eurasian continents, there are so limited regions in which whether the enough findings of the groundwater recharge taken. And groundwater recharge would change under the climate change conditions. This is come from the IPCC scenarios, calculations, projections in 2040 to 2070. This may show, especially in the mid area of the Eurasian continent, then groundwater recharge may increase in the under the climate change conditions. However, there are not clear data or evidence in which we have already taken. So now I would like to show you about the importance of the groundwater and surface water interactions. In here, the river water or surface water level is higher than the groundwater table level. Then the river or surface water may recharge the groundwaters. On the other hand, here, the surface water table is lower than the groundwater table. Then the groundwater discharge to the surface waters. Therefore, we need to know such kind of interactions to get enough knowledge about the groundwater recharge source. For that objectives or perspective, we needed to get the basic three components to show the groundwater flow system or hydrological cycle system. One is source of the waters. Where does that water come from? The source. And the second, where does water come from or come through? The pathway. And how long does it take? The time. So source, path, and times are most important principal factors to decide the groundwater and hydrological cycle system to investigate. So we needed to know these components. For that perspective, we may use some tracing elements like isotopes and the solutions and gases. So multiple tracing elements cycles with groundwater and hydrological cycle. Therefore, we need to use that. And if we have a final output of the groundwater or surface waters, the waters, and sourced from multiple candidates of the recharge source, for example, rain, reservoir water, and groundwater in headwaters, then if we use those tracing elements, then we can evaluate the contribution ratio of each component to the total or final outputs. So coming to the UNESCO Chair on Sustainable Groundwater Management in Mongolia, launched in 2007. So we continuously performing monitoring of the groundwater regarding the, or more focusing on the groundwater and surface water interactions. Many colleagues commit to the monitoring and the observations activities, including Dr. Oduslan and Dr. Chinzorik as one of the best friends in Mongolia. So looking at two rivers here, flowing from east to the west, and there are so many wells to get the groundwaters for pipe waters. As you may know, basically the pipe waters or tap waters, mostly coming from the groundwaters, taken in the floodplain of the two rivers. So basically, many people has said that those groundwaters coming from the two rivers. However, there haven't yet very clear evidences. Therefore, based on the UNESCO chair activities, we perform the intensive sampling of the groundwater and two river waters to specify the recharge source of those groundwaters. So this is a cross sections, north to the south, north to the south of the two river here, and the lane by gravel and sand with a depth or thickness of approximately 30 or 40 meters here. So many groundwater wells are taken the waters at the sand and sand loam geological layers. To river photograph, and there is a here wells to take the groundwater for pipe distributions and floodplain area of the two river. Okay, so this graph shows a contour line of the groundwater table along with the two river in May 2013 and August 2010. Both clearly shows the groundwater flows from east to the west with a little bit angle to the north from the south. May suggest or show clearly the groundwater coming from the two rivers. Okay, so this hydrometric data clearly shows the groundwater flows from the two rivers to the northwest. So how about the chemical tracing components? The diagram shows a spatial distribution of characteristics, water qualities, and stable isotopic composition oxygenating, including sodium, potassium, calcium, magnesium, chloride, and bicarbonate, sulfate, nitrate here. In the surface water of the two rivers here, it's relatively smaller or lower solute concentrations in every ion. On the other hand, groundwaters in the headwater region is north, especially the higher concentrations. And also here, the two river water shows very low oxygenating isotopic ratios. As compared with that, the headwater regions groundwaters. In addition to that, recently, Dr. Hydroscience published one paper. She took observations in a wider area of the two river basins and groundwaters here and river and spring waters there, including many components. So using this data, we evaluate the role of the two river waters and groundwater North Mountain headwater regions and groundwater in the South Mountain headwater regions to the groundwater in the floodplain of the two rivers. In the spring 2013 here, the dominant areas of the groundwater in the South Mountains contributes to the groundwater in the here floodplains. In the spring seasons, just melting seasons. And how about the summer seasons? Here, the dominant, meaning the more than 75% waters in the groundwaters in the floodplains recharged by the two river waters. This is a very clear evidence. Major groundwaters sourced from two rivers. Schematically, the pumping wells here, along with the two rivers there, these waters going to the pipeline for the daily use drinking waters for the Ulaanbaatar city areas is mostly or dominantly coming from the two rivers here. Okay, so the two river water is a major source of the groundwaters for drinking, sustained drinking water in Ulaanbaatar. And here, this is a diagram JICA showing the planned dam in the headwater regions, territory rivers here. But if the dam constructed, then might be the two river waters draw down, then reaching to drawdown of the groundwater level, then it would be not good plan for considering the natural groundwater recharge system. So before closing my talk, I would like to summarize my conclusions. The groundwater is the largest liquid fresh water resource on the earth, and more than 50% of the world population depends on the groundwaters for daily use. And the surface water is important as a source of the groundwaters recharge, especially in the semi-arid and arid regions, especially Ulaanbaatar two river regions. And groundwater surface water system, cycle system is the very key to consider for sustainable integrated water management. Then monitoring of the groundwater should be considered or conducted continuously at certain locations, considering groundwater surface water interactions. So I would like to appreciate greatly for all colleagues who support the activities groundwater sustainable management. Thank you very much for your attention.
Thank you, Professor Maki Tsujimura. So I think we have plenty of time for the questions.
You don't have to.
Yes, you have a question.
Би хөдөө аж ахуйн сургуулийн зөвлөх профессор баран чулуун гэж хүн байна. Энэ сая илтгэл сонирхолтой илтгэл байна. Тэгэхдээ тантай нэг зүйл дээр би бас нэг сайн санал нийлэхгүй байна. Яагаад бол туулголдоор ус хөрөмтлүүлэх бомбт бариад хиймэл нуур үүсгэснээс болоод туулгодын газрын доорх усны түвшин одоо хомсдох багасах магадлалтай гэж та ярьж байна. Би бол энэний эсрэг байгаа юм. Яагадгүй л яг ийм жишээ Говьлтай аймгийн тайшрын усан цахилгаан станцыг барих үед бол яригдж ирсэн. Гэтэл одоо тэр усан цахилгаан станц баригдаад тайшрын гэгээ нуур үүссэн. Тэрнээс хэдий тийм боловч тэр нуураас доош завхан голын дагуух газрын доорх усны түвшин бол ер нь юугаагүй багасаагүй. Харин ч одоо нэмэгдэх тийм хандлагатай болсон. Тэр нэмэгдсэн боломжийг ашиглаад өнөөдөр Говьлтай аймгийн төв рүү 46 км урт шугам хоолой татаад тэндээс аймгийн төвийг усаар хангах ийм ажиллагаа арга хэмжээ авагдаад сүүлийн 3-4 жил болж байгаа юм. Тэгэхээр та бүхнийг зөвхөн энэ судалгааныхаа ажилд дахиж эргэж нэг нягтлж хандаасаа гэж бодож байгаа юм. Яагаад гэвэл ЮНЕСКОгийн судалгааны багаас одоо туул голын дээр ус хөрөмтлүүлэх далан барих нь туулын газрын доорх усны нөөцөд сөргөөр нөлөөлнө гэсэн ийм дүгнэлт мессеж өгөх юм бол яванда маш олон жилийн хугацаанд үндсэндээ 1980-70-аад оноос хойш одоо туул голдоор бомбд барих нь зөв буруу юу гэсэн маргаантай байгаа энэ нөхцөл магадгүй нийгэмд одоо буруу ойлголт төрүүлэх ихээхэн том мессеж болж магадгүй гэдэг дээр би болгоомжилж байна. Баярлалаа танд.
So, Mr. Convener, could you please translate in English? Actually, my translation system doesn't work. So I'm sorry, but I don't understand his saying.
Sorry about that.
Oh, Dr. Chinzorik, could you please translate for me? Or
yes, Professor.
Yep.
Yeah, he is asking about if we construct a dam upstream of the tall river basin, then it may be impact on the groundwater. You conclude that if we construct a dam upstream of the tall river, it may be impact on the groundwater to decline the water table. But he doesn't agree this situations. Yeah, it's why you conclude that if we construct a dam on the upstream of the tall river, then the downstream groundwater table will be decline, maybe decline. Why?
Okay. Okay, thank you. I understand his questions. And I would say the groundwater in the downstream recharged by the two river waters. Okay, so if the dam constructed in the upper stream regions, then the river water level in the downstreams draw down because the dam should control the water level of the two river. Therefore, due to the drawdown of the two river waters in the downstream, then should affect on the groundwater recharge clearly. Therefore, I would say the dam construction may affect on the groundwater recharge in the downstream. The dam should control the water level, even in downstream regions. The data or evidence clearly shows that processes. Thank you for your questions.
Орчуулга явуулсан болов уу? Тэгээд яах вэ? Энэ юу Professor?
Hi.
I have
Yes.
question, one questions.
Dr. Sarantia-san.
Yeah, so I'm sorry to come into this discussion, but well, I'm Mongolian, so I had this chance to listen to both the participant, Dr. Baranchulong, who asked the question. So his point was that your conclusion may give a wrong message to people who might have an impression that UNESCO is not supporting the government plans to build reservoirs upstream to the river. And actually, he gave an example that Taisher hydropower dam, the example of that in the, maybe you know about this in Govelta province, and the reservoir, which is called Gegen Lake, has been replenished since a few years ago, and they have observed that the groundwater table downstream in Zafan River didn't decline, but actually there is a tendency that the groundwater level might have increased. So this example shows that maybe the groundwater in Tole River will not decline if reservoirs upstream will be built. So the consideration of building dams upstream to the river has been in discussion since the 1970s. So if UNESCO UNESCO affiliated research team gives this conclusion, this might give a message that people will not support this construction idea. So he is recommending you to maybe look at the example of Taisher reservoir, Gegen reservoir, and to observe whether your conclusion that the reservoirs built upstream to the river will really impact the groundwater level decline in Tole River. So that was his recommendation. And actually now my comment is that Ulaanbaatar city will face water problem in the coming decade. You know, the population of the city is growing and water demand is growing, and the current capacity will not be able to meet water demand. So the city has to find no new source of water. So that is, they have to have either to build reservoirs or to develop new sources, groundwater resources, much further than the current water supply area. So I think that is a question for the city and the country to address.
Okay, thank you for your supporting or suggestions. I understand that they are thinking and bad. Yes, I know that. And basically, the data shows the groundwaters in the Ulaanbaatar city areas is coming from recharged by the two river waters. That is a fact. So you shouldn't ignore that. You shouldn't ignore that. So based on that, understanding that, then you should consider the future perspective. So this is a data. This is a data. So you can decide, or you should decide, considering the data. This is a fact and the data. Okay. So I would say you should consider that. You should decide that, not me. This is the data and fact. Thank you.
All right. Thank you again, Professor Maki Tsujimura. And sorry about the translation system didn't work in your side. And
no problem.
For those who interpreted the question and answer. So let's move to the next presentation. Our next speaker is Dr. Jan Friesen. And title of his work is Water Sensitive Infrastructure Planning. So please welcome.
Good afternoon. Thank you very much for the kind invitation to this conference. I will introduce to you today our work on water sensitive infrastructure planning, and we will mostly be introducing wastewater management infrastructure planning along different decentralization gradients and across different scales from the local scale up to the regional and even the global scale. Thank you. Okay. So, yeah. So our motivation to plan water infrastructure, I think one of the previous talks introduced the United Nations Development Goals. So we're working on the development goal number 6 on clean water and sanitation in terms of wastewater management. That's mostly relevant for rural regions with low connection degrees that often also coincides with low economy regions. In that sense, it aids towards resource protection. We heard about groundwater before, so proper wastewater management, of course, also protects groundwater resources. And especially in low-income regions, cost assessment or cost efficiency is very important. On another sense, in terms of infrastructure planning, we also work on the United Nations Sustainable Development Goals number 11 on sustainable cities and communities. In these areas, we're not so much talking about decentral or semi-central wastewater management, but more about stormwater management and about drought. I will be focusing on the first part, wastewater management, but the following talk by my colleague, Ganbata Kuelbata, will focus on urban stormwater management. Now, the tools that we develop are mostly preliminary planning tools. So we do not work on detailed planning, but more on master planning to provide cost estimates for different predefined wastewater management scenarios. These scenarios, which I will explain in some case studies, allow both as a basis for a stakeholder discussion, and also the development of plausible scenarios can be already an input of an early stakeholder involvement. And these scenarios, from our point of view, are not only guideline-based according to, in our case, German regulations or specific country regulations, but also in view of climate change, resource-efficient scenarios that may not yet be conform with local standards, but of course offer an opportunity to identify gaps that could be closed. Now we do that across different scales, one at the settlement scale, but also at the regional scale, looking at, in one case, specific villages or at whole administrative regions. And we work with, usually we start out with globally available data, so often also proxy data. But in all of our tools, we also have the opportunity to replace global data with local data, for example, local cost data or high resolution elevation models. Because I'm talking about decentral wastewater infrastructure planning, I just one slide to sort of set the scene here. On one side, we have centralized systems where a whole city or a whole region is connected to a single treatment plant that can also be a cluster of several settlements and can go up to relatively large plants. One of the world's largest plant at the moment is the Bar el-Bakka water treatment plant near Cairo in Egypt, which treats an equivalent of up to 35 million person equivalent. On the other end of the scale, we have decentral systems. They start maybe as the household scale, where you have 4 to 10 inhabitants, but can also go up to clusters of suburbs or villages up to maybe 5 or 10,000 population. And in this view, we now developed a planning tool that works along different scenarios. So from centralized to semi-centralized, decentralized, as well as an on-site or tanker solution. And this tool is also automated in the way that we have automated the data processing, that we automated a cost module for the cost assessment. And I will now go into some details of this tool. So first, for example, the scenarios that in this case are developed along a decentralization gradient. So for example, scenario 2 is a semi-centralized scenario where the whole village has one central sewer network and is connected to one treatment station. Then we have a decentralized scenario where different clusters are defined, which you may see, here, with individual treatment plants, which can then also be used, for example, for local reuse. And then we have completely decentral scenarios where each house is served by tankers, or each household has a unique on-site treatment. And now to start with this, we often start with a centralized scenario. So the data that we use for this is road data, which we often take from globally available data sources like OpenStreetMap data, elevation data, buildings and population. And using that, we start out with generating a central sewer network based on elevation and based on the fact that we aim or we optimize the system towards gravity flow. So where we need pumping stations, we include pumping stations, but the automated sewer generator is tuned towards as little pumping stations as possible. From this system, we decentralize. So we look at different, we try to identify clusters in the villages. These clusters are based on building density and on specific sewer length. And using the specific sewer length and the building density, we can then have a cost-based estimate or a cost-based threshold of for which building density an on-site solution is feasible and for which a cluster system is feasible. And what you see here, the gray shaded areas are cluster systems, and the blue dots would then receive on-site treatment. This sort of spatial results are then handed over to a cost assessment, to a life cycle cost assessment, where we then calculate all the costs, including investment costs, reinvestment costs, but also operation and maintenance costs over the life cycle of 60 years, which is often the life cycle of a typical sewer. And for that we then combine with scenario numbers. Those are the numbers from the spatial scenario, and a list of costs, which then of course can also be used for local costs, so the cost of sewer manholes, wastewater treatment plants, operation and maintenance. And at the end, we get a cost ranking of these different scenarios, so we also get the most cost-efficient scenario, which can of course then be discussed with the stakeholders or with the water company, because as you can see on the figure here, some scenarios are relatively close together. So it's then also a question of what the additional benefits of these scenarios or the plausibility of these scenarios are. Another tool we developed goes to scale up. This is an example from Jordan where we go to the regional scale. And in this case, we have only two scenarios, a centralized and a decentralized, with a view that the decentralized scenario is a very specific reuse scenario. So in the decentralized scenario, we also link agricultural reuse to it. And if we go for a whole country where we have not, for example, all housing data, we also look at some proxy data like a road sewer length relationship that you see at the bottom here, which is basically a tool to estimate the amount of sewer that we need. And then we can again use our cost estimates to compare the different scenarios. Now going one scale up, we also look the other way. So The objective of the octopus tool was to find out how far, not how far can we decentralize, but how far does it make to centralize? So to combine cities or villages into larger wastewater treatment clusters. And on top of that, we also do this on a global scale. And the simple behind that is relatively simple. So you have, for example, 2 villages, one with 2,000 inhabitants, one with 100 inhabitants, with a similar water, with the same water consumption. We can calculate the wastewater treatment plant investment costs, the operation and maintenance costs. And using the economy of scale, we can then basically find out how much costs do we reduce when we combine these 2 villages. So the economy of scale in this sense means that the larger the wastewater treatment plant, the lower the cost. And that is not only for the investment cost, but also for the operation and maintenance costs. And that means for us that in the example of these 2 villages, we have a larger settlement of 5,000 population, and which would give us, compared to the 2 individual plants, a saving of, in this case, 1.6, 1.8 million euros. And the question now is that enough to connect the 2 villages so that we can actually have a wastewater treatment cluster? And whereas this example is relatively easy to calculate, you only have 2 villages, you have the distance, that becomes a little bit more complicated if you go to administrational regions which with a large number of settlements. So what we did here is we took 140 countries with about over 4 million settlements, and we used a greedy graph algorithm to optimize these networks. And what you see in the animation below is basically the algorithm that checks for each connection if, by increasing the wastewater treatment size, you can afford the additional sewer network to connect these villages. And on this side, you also see a result for a region in Tunisia. It's a governorate in Tunisia, and the black dots and the network shows the optimized network. The red dots show the wastewater treatment plants for these networks, and the small black dots that don't have a connection, they do not make sense to be connected cost-wise. And this is a view of the results at a global level. So what we can do now is we can not only show how many clusters make sense, but also how much savings, in addition to clustering, you can generate. And this was displayed in percent. And what we can see, if we look at all 140 countries, we can see that there is a substantial cost reduction of about 10% for more than 20% of all the analyzed regions. And with that, I'm already concluding the talk. So I've shown 3 different tools, from the settlement scale to the regional to the global scale, to use different methods to optimize wastewater management, clustering, and wastewater management scenarios. And this is important, one, for water master planning, to identify which scenarios should go into a detailed planning. Then, of course, these tools can also be used for local and regional wastewater availability, and couple them also to wastewater or treated effluent demand, if you think about reuse and irrigation water. And of course, it helps us using big data to also cope with data scarcity. Thank you very much.
Thank you. So I think we have a time for 2 to 3 questions. Is there any question? I'm not sure if there's a question on the Zoom chat. Okay, thank you very much. The next speaker is Dr. Gambatar. So he's going to present on what must be approach for the management of urban stormwater at block level.
За сайн бацгаанууд гэд та бүхэнд өнөөдрийн мэндийг хүргэе. Тэгээд өнөөдрийн үйл ажиллагаанд оролцуулах бидрийг урьж оролцуулж байгаад маш их баярлалаа гэж хэлсэн юм аа. Тэгээд би өөрөө шүтээсийг бас 2011 онд төгссөн. Тэгээд дараа нь болохоор Германы Баухаус их сургуульд Цорын газрын усны менежментийн чиглэлээр докторийн зориг хамгаалсан. Өнөөдөр миний ярих гэж байгаа сэдв болохоор презентац руу орохдоо би англиар яриад явчих гэж бодсон. Яг тэгэхээр энэ ажлыг дандаа тухайн хэл дээр нь хийгээд үр дүнгийн тухайн хэл дээр нь гаргасан болохоор. So yeah, the management of urban stormwater at block level, the name occasionally fits quite good to this to the acronym of the university, yeah, must, and again, must here. However, we have this must be for block level. It was a new approach to developed by us to look at the potentials of decentralized stormwater management systems in existing cities. What is the problem? So when we have natural landscapes, and if there is a rain, we have slow pattern or runoff pattern, which is not that steep, but long. But as soon as we start to build cities upon that and seal the surfaces, this runoff pattern is changed. So it becomes much more steep and short, which means we have a flooding risks. Also, at the end, we have water deficit. The city doesn't have the water anymore when we need that. So this problem is again exacerbated by climate change, where now the intensity of the storm events are increasing. So the climate change is working not for us, but against us. And this we want to change. So by creating potential or creating rooms and blue-green infrastructure, infiltration possibilities within these urban areas to bring down this red curve back to the natural pattern. So what exactly do we understand under blue-green infrastructure? So green infrastructure is, according to the US EPA, is incorporation of natural landscape into urban spaces. So these natural landscape becomes, green infrastructure becomes blue-green infrastructure as soon as it gets some role for urban water management. Then we call that blue-green infrastructure. We had one project in Leipzig, the city where the research institute is located. And we had a study area of around 800 hectares in the north of the city. The city also faces every now and then severe storm events and therefore also floods. And the idea was how to assess the potentials of the blue-green infrastructure or potential reduction of the surface runoff by using the blue-green infrastructure. So we came up with the idea to divide the city into modular units so that we can very easily scale up and down, because usually these modeling processes are quite complex. This urban environment is very huge and very complex. One big environment. So we wanted to divide that, break that into very simple modular units. So we can compute whether it's just 1 unit or 1,000 units, exactly the same process on each unit. And therefore we came up with this urban block concept. We divided the city into blocks. The blocks basically are circumferred by the streets. And then we looked at the surface classification types. So we looked at the how big is the green area and how big is the sealed surface. This would indicate us how much the surface runoff during the storm events would be. And then we started to collect the data, format them in GIS environment, and started carrying out our modeling. And we also used some infiltration or retention infrastructure, for example, surface infiltration. Basically, the rainwater will be just spread on evenly managed surface so that it can infiltrate to the groundwater. We also have swale infiltration. It will increase the retention capacity by just enabling some storage on top of the surfaces. And we have also bioretention cell. It has a much higher capacity underneath a swale infiltration. And of course, we have the trench infiltration. It's a subsurface technology where the water is, the storm water is stored underneath or underground. And of course, we have green roof, which has the potential of retaining the water for certain times. And shaft infiltration is actually more of a gray infrastructure, but it has much higher storage and infiltration capacity compared to the other infrastructures. And one thing at the Institute is we have this blue-green infrastructure also installed so that we can generate our data to calibrate the models. And then these infrastructure were built into modeling programs, in this case, microurban, but we can also use SWIM, which is free to use program. And that is some examples of our results. So these colors would just indicate how critical this block is. The red means this block has a very high portion of sealed surface compared to green area. Yeah? And this picture shows in case of no rain, but as soon as we have a 5 years rain event for 2 hours, so in total there is around 30 millimeters of rainwater falling down on our study area. We looked at this very permeable soil, and then we will have around 200,000 cubic meter of rainwater or surface rainwater we have to deal with, and almost 50% of the rainwater turns into surface runoff. Yeah? This would mean our existing infrastructure, such as sewer network or even roads, might be overloaded or even damaged. The columns here, these are just shown for the purpose of presentation, not that the city stands under like 100-meter water column. And we increased the rain intensity from 5 to 30 years. We can also see that the runoff increases from each block. Even we looked at the 100 years storm event, and each time we also come up with the results that almost 50% of the rainwater is turning into surface runoff. So let's go back to the 30 years rain event for 2 hours. So it's around 50 millimeters of precipitation. And then we looked at the bioretention cell. For each block, we simulated these retention and infiltration infrastructure, which is a decentral one. And the results were quite surprising. Only few blocks remained producing surface runoff, because these blocks, they couldn't contain any blue-green infrastructure because there was no enough space. Yeah? But in general, we could reduce this high amount of surface runoff from 150,000 cubic meters within 2 hours to 1,000 cubic meters, so almost 99% reduction. And this showed us that even the existing infrastructure or existing cities, they might have very high potential to include this kind of infrastructure in order to reduce the urban runoff, surface runoff. And we also developed a long-term analysis. Yeah? What exactly means these blue-green infrastructure for our city or for our river? And then we looked at the combined sewer overflow events. This was the outflow point, and what we can see here is when we do nothing, this is the current state, yeah, the water or combined sewer overflow, both in terms of hydraulic and pollution loads, are shown here 100%. But as soon as we start building this kind of infrastructure for very small rain events, we can see there is a very high reduction rate in terms of discharge volume and pollution load. But what we found very interesting was that even when we increased the size of this infrastructure, designing it for 100 years of rain event, the difference between very small infrastructure compared to the very big infrastructure over a long period of time was very small compared to doing nothing and having a small infrastructure there. So, yeah, as a conclusion, we managed to divide this very complex urban area, which usually require quite complicated hydraulic and hydrologic analysis into a very simple modular units so that we can just scale up and down. And we have seen there is a high potential to avoid floods within the urban environment. Also high potential to avoid pollution discharges. And we have seen that smaller blue-green infrastructure have overproportionate impact in long term. And now we are trying to work in UB city or adapt our tool for Ulaanbaatar city. And we already started the analysis. So we divided the city of Ulaanbaatar into urban blocks. And once we create some results, we will call it not must be, but must you be. And we also are interested in cooperations with local partners to look at different strategy to adapt this kind of blue-green infrastructure there, how it would like in Mongolian conditions, because we have way different climatic conditions here. So with that, I would like to thank you very much. And yeah, if you have questions, then I would be glad to answer.
Thank you, Dr. Ulaanbaatar. Yes, we have enough time for the question. Okay.
За сонирхолтой илтгэл тавьсан явдал баярлалаа Гаанбаатар шавьда. Сайн явж ирсэн үү? Тэгээд та хэд Улаанбаатар хотын нийслэлийн засаг даргын хамгааллын газартай хамтарч ажиллахаар одоо ярилцж байгаа юу? Эсвэл одоо ямар нэгэн төрийн бус байгууллага энтертэй одоо хамтарч ажиллахаар төлөвлөж байгаа юу? Тэгээ миний бодлоор бол танай энэ судалгааны дүн Улаанбаатар хотын төлөвлөлтөнд энийг тусгахад маш их үр дүнтэй байх болно. Одоогийн үерийн хамгаалтын одоо сувгшуудуу барьж байгаа энэ бүх юмнууд ч энэс өөр одоо системээр явж байгаа шүү дээ. Тэгээд энэ системүүдийг нэвтрүүлбэл Улаанбаатар хотыг үерийн одоо аюул жил болгон нэрвэгдэж байдаг энэс хөндөрүүлчих одоо бас нэг ангижруулах гол арга зам байж магадгүй гэж харж байна л байж энэ илтгэлээс баярлалаа.
За баярлалаа гэж. Юу бид нар болохоор ерөнхийдөө нөгөө одоо судалгаагаа дөнгөж эхэлчээд явж байгаа тий. Тэгээд эн чинь болохоор яг хамтарч ажиллах байгууллага тэгээд судалгааны төвүүдийг хайж байгаа байхгүй. Тэгээд яг хуу шүтист таньдаг хүмүүсээр ингээд дамжуулаад яг эхний одоо юм контакт үсээд өнөөдөр энэ хурал дээр ингээд хурж ирэх боломж олдчоод тэгээд бас энэ боломжинд бид нар айгүйх баярлаад одоохондоо бол байж байгаа юм л да. Тэгээд ерөнхий одоо төлөвлөгөө яаж одоо дараагийнхаа ажлыг хийх вэ гэсэн төлөвлөгөө бол эхлээд одоо энэ шүтээсийн одоо энэ барилга архитектур их сургуулийн хүмүүстэйгээ сайн ярилцаад илүү наривчлалтаа дата юу вэ гэдэг дээр сайн санал бодлоо ингээд хуваалцж хагаад тэгээд эдрээрээ дамжуулаад нэг хэдэн одоо хот төлөвлөлтийн тий Улаанбаатар хотын захиргааны ийм одоо шийдвэр гаргагч нартай бас уулзуул яах болоо гэсэн тийм найдвартай ирсэн байхгүй юу. Тэгээ тэрнээс бол яг төлөвлөгөө бол одоохондоо байхгүй л. Тэ.
Давагдэрж манай усны эрчим компани өөр хоёр компанитай нийлээд 2015-аас 13-аас 15 онд Улаанбаатарт үерийн эрсдлийн үнэлгээ гэж хийсэн байгаа. Тэр асуудал өөртөө чинь одоо танилцсан уугүй юу? Тэр үерийн эрсдлийн үнэлгээ. Энэ бол Дэлхийн банкны санхүүжилтээр хийгдсэн том төсөл байгаа. Хотын нийтийн аж ахуйн төслийн газарт бид 24 том материал хүлээлгээд өгсөн байж байгаа. Энэ материалаас танилцсан уу? Өөрийн ажилтай чи яаж холбогдох юм бэ гэж.
Одоохондоо бол танилцж амжаагүй гоо. Түрүү хэлсэн одоо энэ судалгаа яг одоо Монголыг одоо хамрах Улаанбаатар хотыг дээр хийж байгаа судалгаа бол эхлээд удаагүй байгаа болохоор тий. Гэхдээ хэрвээ тийм судалгаа аль хэдийн хийгдсэн байгаа бол ер нь тэр судалгааг өөрсдийнхөө судалгаанд ингээ ашиглах тийм сонирхол бол их өндөр байгаа.
Хэд асуулт байгаа. Okay, so there's no question. Thank you, Dr. Ambatar again. And so we are going to invite our last speaker of the session, as well as of the conference. So it will be given by Dr. Chinzer. He's going to present us on challenges for hydro-peaking mitigation in an ice-covered river, a case study of Ig hydroelectric plant, Mongolia.
За бүгдэнд энэ өдрийн мэндийг хүргэе. Би усны барилга байгууламжийн мэргэжилтийн 2007 онд шүтээсийн барилгын сургуулийг энэ мэргэжлэр төгссөн байна. За үүнээс хойш шинжлэх ухааны академийн геоэкологи өөрчлөлт, газар зүйн геоэкологи өөрчлөлтийн усны нөөц усагчдын салбарт эрдэм шинжилгээний ажилтан салбарын даргаар ажиллаж байна. За олон улсын хурал учраас мөн англиар чадан ядан тавихыг тавина. Энэ судалгааны ажил бол энэ эгийн голлын жишээн дээр хийсэн. Эгийн гол дээр энэ оргил ачааллын урсцыг зохицуулах тухай хэрхэн оргил ачааллын урсцыг байгальд халуугаар одоо арга хэмжээ авах тухай ийм өгүүлэл судалгааны ажил байгаамаа. За ингээд good afternoon everybody. This is a presentation title I'm going to speak, the hydropicking mitigation in ice covered river, case study egg hydropower plant. Yeah, contents. I will going to talk about the introduction part, method, result, and conclusions. Most of you know about the egg hydropower plant. The egg hydropower plant is planning to construct on the Egg River, the upstream of about 2.5 kilometer upstream of the confluence of the жилийн and Egg River. This is a egg hydropower plant is planned to be constructed on the lower course of the Egg River. The total capacity of the power plant will be 315 megawatt, and the plant will be equipped with 6 Francis turbines. The volume and water surface area of the reservoir at the normal water level will be approximately 5.7 billion cubic meter and 154.3 square kilometer respectively. There are a lot of advantages if we construct the egg hydropower plant. This is renewable energy. Then second, we can reduce the greenhouse gases. Then we can save clean water. We can save, accumulate the surface water. So there are a lot of advantage if we construct the egg hydropower. We can manage the water resource. We can irrigate in downstream part, improve the irrigation systems, also supply the clean water to the cities, the center settlements area. So we can develop the tourisms near the reservoir, the power plant. But this is a picture shows this electricity usage, and in Mongolia, in time, this is 24 hours. Around the 5 o'clock, the electricity demand increased. Then it's continuously increased in 6 p.m., 7 p.m., 8 p.m., and 9 p.m. Then again, it's reducing because this is fluctuations. The night time, mostly it is 6 to 9 p.m. The electricity demand is increasing. We are, but our capacity of the power plant cannot supply these fluctuations. Therefore, we export some electricity is imported from Russia and China. Yes, this hydropower plant, the advantage is to meet these fluctuations. The hydropower plant, if we construct a plant, we just turn on the bottom, then it's working, they generate the electricity. Then if you want to turn off, then just put the bottom, then it's shut down. It's very quick. This is this planning, operation planning, hydropower plant, egg. The time is electricity generation from 12 a.m. to 5 p.m. It's operation will be the around the 40 megawatt hours. Then I said before the previous slide, the night time around the 6 o'clock and 7 o'clock, 8 p.m. The electricity hydropower plant planning to generate 315 megawatt this pool capacity. It will work. That time the turbine discharge, you can see this turbine discharge. If it, the night time turbine discharge as downstream flow around 58 cubic meter per second. Then night time to about around the 6, 7, 8 o'clock, the discharge suddenly increased to 458 meter cubic second. This is a winter operation of egg hydropower plant, winter, from November to March. This fluctuation is repeated every day. It's a downstream flow is suddenly increased nighttime, then midnight or tomorrow morning, it's the flow decreasing. Then it's again increasing the night, then it again decreases. This is very, maybe it's a very high impact on the river ecosystem, some fish, some this macro elements. This is the example of the northern shevet. This natural flow is this this is a natural flow. After the dam construction, the downstream flow looks like that because of the electricity generations. It will be occur in egg hydropower plant. But we can mitigate this impact. This is example. As a European countries, this is 0.8 cubic meter per second is the base operations. Then hydro peaking, it will be reached 70 cubic per seconds. It will be repeated every day. It looks like that. Sometimes river dry, sometimes looks like flooding. It's repeating every. It's maybe impact on ecosystem of river ecosystems. Yeah, this line is base operations. This blue line is peak operation. It's repeating. This is, here is some, we can see some die fish here maybe. This study was performed in downstream of the egg hydropower plant on the Жилийн River. The study reach is 40.1 kilometer long reach of the Жилийн River located in downstream. Yeah. Then in this study, I have developed 3 scenarios, then developed 2 models. The first model was Heck regime, the reservoir model. The second model was the Heck RAS, the river hydraulic models. Then we evaluated the mitigation measure. Its mitigation measure is the Booper Dam. Booper Dam is planning to construct downstream of the main dam. Here it's okay. Here. Then I simulated the model, develop model. Here, this is natural situations. There is nothing to nothing. Here, just main dam is constructed. Then I simulated the river hydraulic parameters. Then after that, we construct a model with Booper Dam. Then we see the parameters. They compare to evaluate the Booper Dam. Is Booper Dam good or not good? Yeah, this is just development of construction of the HICRAS model. This is study the HICRAS model. HICRAS model is the river hydraulic model. HICRAS model shows results. Simulates the hydraulic parameters. Yes, this is winter operation. Winter operation here, the 12 a.m. to 5 p.m. it's base load. Then when electricity demand increase, it produces the electricity. Here it's like, this is the down picture. The below picture is the turbine discharge. Also, turbine discharge is the night time. It's and tomorrow 5 p.m. it's base flow. Then suddenly increase up to 458 cubic meter per second. It's repeated every day from November to March. It looks like that. Here, this black line shows natural flow. Natural flow. This blue line shows downstream of flow of the egg hydropower plant. It looks like changing flow in downstream like that. Then buffer dam will be just planning to construct just downstream of the main dam, the downstream of the hydropower plant. This is a small dam. This is a buffer dam. Purpose of the buffer dam is to mitigate hydropeaking of the egg hydropower plant. This is a structural mitigation measure. The purpose of the buffer dam is to pick up hydropeaking flows, this peak flow, and release the water smoothly downstream, thus reducing the negative ecological impact in downstream. The buffer dam, it's like if we construct buffer dam in downstream, the flow, the regulated flow, this hydropower plant downstream flow, it is blue line. It looks like that. It's the buffer dam can mitigate the measure, mitigate this impact. Yes, we simulated the hydraulic parameters. The buffer dam is very much advantage to reduce the impact of the hydropower plant operations on in the ecosystems. Yeah, buffer dam. Then conclusion here. The conclusions for electricity production at this selected power plant show that the highest hydropeaking will be occur during winter time when the river flow is usually low. Through the combination of the reservoir and hydraulic modeling, it could be shown that the buffer dam could completely eliminate hydropeaking waves. Highly variable magnitudes of the hydraulic parameters, for example, the flow velocity and bed shear stress were satisfactorily reduced with the operation of the buffer dam. The mitigated flow with the buffer dam will be improved the habitat conditions for the local aquatic organisms, which largely depend on the hydraulic parameters. Okay, thank you.
Thank you, Dr. Chinzerg. So we have a time for the questions.
Надад нэг юм асуудал байна. Энэ эгийн голын усан цахилгаан станцын анхны төслийг хийсэн хүний хувьд энэ өөрийн чинь ажил дараагийн төсөл дээр юм байна гэж ойлголоо. 315 мегаваттын төсөл юм байна гэж. Тэгсэн чинь зөвхөн 2016 оны ачаал дээр хийсэн байна. Тэгэхээр зэрэг 2016-аас хойш одоо 2024 он болоод 8 жил болчиход нөгөөд манай төв эрчим хүчний системийн ачаалал 1484 мегаватт болцсон шүү дээ. Тэгэхээр зэрэг энэ график юунууд чинь бүгд шинжлэгдэх үү яах вэ гэдэг асуудал байна. Нэгдүгээр асуудал. Хоёрдугаар асуудал 315 мегаватт ажиллаж байхад 456 куб метр секунд гэж гаргасан байна. 458 метр куб секунд. Энэ арай л бага юм үзэгдээд байна. 600 орчим куб метр секунд ус явах ёстой доошоо. Тэгэхээр зэрэг нөгөө голдрол маань 230 куб метр ус гаргах чадвартай тийм голдрлоор 600 куб метр секунд ус явахаа зэрэг ямар аюул учрах уу гэдгийг бас бодох хэрэгтэй байдаг. Энийг одоо цаашид бодож үзэх үү яах вэ гэдэг асуудал байна.
За баярлалаа. Тэгээ эрчим хүчний хэрэгцээ бол жил ирэх тусам өсөж байгаа. Тэгээ энэ судалгааны тэгээд эгийн голын усан цахилгаан станцыг төлөвлөхдөө яг тухайн үеийн эрчим хүчний ачаалал хэтийн төлөөс харж агаад энэ юуг ашиглалтын гормыг гаргасан болов гэж бодож байгаа. За дараагийнх нь энэ манай яг өвлийн хэрэгцээ бол маш их байна л да. Өвлийн цахилгааны энэ горим хэрэглээ бол маш ихтэй. Ялангуяа шөнийн цагт, оройны цагт айд болон одоо цахилгаан хэрэгслээ асаадаг учраас энэ ингээд маш их өндөр одоо 4 цагийн хугацаанд 5-аас 9 цагийн хугацаанд маш их өндөр хэрэглээ учраас энэ хэлбэлцэл үүсээд байна л да. Усан цахилгаан станц бол энэ хэлбэлцлийг хаахад бол маш чухал ач холбогдолтой байдаг. Тэгтэл манай Монгол орны нөхцөлд бол өвлөл гэдэг бол ерөөсөө хамгийн бага урсгалтай үз байдаггүй. Энэ хоёр хоорондоо зөрчилдөд байх шиг байна. Өвөл бид нар илүү их цахилгаан үйлдвэрлэх хэрэг шаардлага гараад идэг. Тэгэхээр илүү их зарцуулалтаа усыг доош хаях болдог. Тэгтэл голын ус маань хамгийн бага байдаг. Экологийн хувьд ч гэсэн экосистемийн тэрэн тогтсон экосистем байж идэг байдаг юм байна. Энэ учраас бас хүндрэлтэй л байгаа л да. Энэ бас хүндрэлтэй нөхцөл байна. Одоо нэг асуудал бол бид нар эрчим хүчний гормоос хамаарч усан цахилгаан станцын ашиглалтын гормыг тохируулах уу, усны нөөцтөөсөө хамаарч эрчим хүчээ тохируулах гэдэг бас ийм асуудал гарч ирээ судалгааны ажлууд хийгдээ явж байгаа болов уу гэж. Тэр голдрлын хувьд бол яг аргагүй. Голдрл бол голдрлын өөрийн ус урсгах хүчин одоо хэмжээ гэж бий. Тэрнээс илүү усыг бас ингээд өвлийн нөхцөлд гарах ийм хүндрэлтэй асуудал бий. Тэгэхдээ энэ далангийн туслан энэ бүпүр буюу туслаг далангийн тусалцаар зарим нэг хүндрэлтэй асуудлыг шийдвэрлэж болж байгаа. Одоо 458 м3 секундээр доошоо ус хаяхад тухайн голдрол бол багтааж чадахгүй өвлийн нөхцөл. За тэрийг бүпүр далан дээрээ буюу туслах далан дээрээ тэр ирж байгаа усыг тогтоон бариад айжмаар 100 м3 секундээр доошоо хаяж болж байгаа 24 цагийн хугацаанд. Ийм зохицуулалт хийгээд энэ нөлөөллүүдийг бууруулах боломж бүрдээд байгаа. Тэгээ судалгааны ажлуудыг хийх шаардлагатай. Энэ эгийн голын усан цахилгаан станцын туслах далан зөвхөн концепц буюу төсөөллийн түвшинд хийгдсэн ажил байна.
За. Надад нэг асуулт байгаа маа. Сайн бацгаана уу? Орой минь дөрвөө. Яг оргил ачааллын урсцыг хангахыг усны зарцуулгыг голын голдрол руу хаях юу гэлээ зохицуулах далан гэж ойлгосон зөв үү? Тэгэхээр энэ яг одоо нөгөө үүсэж байгаа төрөлөнд урсгалыг л ерөнхийдөө хааж байгаа гэсэн үг үстэй тий зохицуулж байгаа гэсэн. Тэгэхээр буцаж яг станцынхаа турбинлуу төрөлт үүсэх боломжтой юу?
тий энэ туслах талангийн одоо зур туслахын ажил тэзүү зур туслахын ажил байхгүй байна. Төсөөллийн төвшөнд ер нь ийм юм байж болох юм байна гэсэн баг хэмжээний тооцоотой ийм тайлан байдгийн байна. Тийм учраас одоо бид нар тэрэнд нөлөөлөхгүй байхаар л ажлын даалгавар өгөөд хэрвээ энэ ажил цаашаа үргэлжлэх юм бол ажлын даалгавар дээрээ хэрвээ туслах талан барих юм бол станцийнхаа барилгад нөлөөлөхгүй шүү төвшин гэсэн тийм ажлын даалгавар өгөөд өгөх шаардлагатай байна. Гол нь
бодит кейс төр болохоор ямар турбинээс хамаарат Францис уу нөгөө Кафлан уу гэдгээс хамаарат турбинээс хамаарат нөгөө буцаж төрөлд үүсдэг тийм тохиолдол бодит кейс төр байдаг л да. Тэгээ тэрийг харин тооцсон юм болов уу үгүй гэж асуух гэсэн.
Одоо бид нэг ажлын даалгаврынхаа хувьд янда тэрийг нөлөөлөхгүй байхаар ажлын даалгавраар хэрвээ энэ ажил явах юм бол би сайн нэг ажилд юу мэдэхгүй байна л энэ ажилд учраас эгийн голын ажиглагаас.
За ингээд 60 жил энэ усны хишээр бэлтгэсэн энэ эрдэмтэн докторудад баяр хүргэе. Ийм сайхан арга хэмжээ зохион байгуулж байгаа талархж байна. Мөн өрсөн явдал талархлаа. За ингээд би энэ аман гол дээр одоо их 15 жил төрийн бас ажиллаж байгаа маа аман гол хамгаална гэдэг. Тэгээ одоо алин болгон хамгаалах вэ бас энийг бас нэг ашиглах хэрэгтэй болов уу гэж бодоод байгаа. Ягаад гэвэл 20 дугаар зууны дундуур 50-аад оны эхээр манай өвөө тэргүүтээ бурятууд усан жижиг оврын усан цахилгаан станц ажиллуулад бан зүсжсэн туршлага бай. Гэтэл 21-р зуунд бид нар чинь анан голоо ашиглаж чадахгүй тэр хөлийн усны хилцээр гэдэг нэг юмд одоо баригдчаад тэгээд одоо энэ ч анан голын ус одоо ингээд хил даваад бүр өчнөн куб метрээр гараа явчихжээ штэ. Тийм учраас одоо энэ усныхаа хилцээрийг нягтлаа тэр хөлийн усныхаа тэгээд энийг одоо жоохон наашраа болгоод анан голынхаа тэр их усыг одоо тэр анан голын сав дагуу байгаа сав газарт амьдарч байгаа 6 сумын иргэд одоо зөө зохистой ашигламаар байна. Тэгээд би бас их олон жил ярьж байгаа л да. Тэгээд одоо яг хөлийн усны хилцээр гэдгээр л одоо тэгээд болдгоомаа гэж байдгийн. Тэгээд одоо аль болгон тэгээ болохгүй байх те. Тэгээд ийм сайхан хурал суулаа маш их арвин туршлага харлаа. Ямар ч ясна нэг аав маань бас нэг жижиг усан цахилгаан станц мөрөөдөл яриад байдгийн. Тэрийг нь хэрэгжүүлж үздэг юм уу гэж бодож байна. За анхаарал тавьсанд баярлалаа.
За ер нь манай усан цахилгаан станцад ганц Монголд энэ өмстэй гардаа баригдаад байгаа юм биш. Манай дээр нь халиад ашиг үүсгэд буруутах юм бас байхгүй. Ганцхан манай нүүдлийн амаалаж нүүдлийнх ингээд чинь голын айс авдагаад өвжөө буусна барьждаг. Тэр нь л мөсөнд орчоод байдаг. Тэрнээс болоод байгаа асуудал шүү дээ. Тэрнээс дэлхийд ярийн гिचнэн том голоод өчнөн оргил ачаалын үед энээс илүү арснууд хаяад болж байгаа нь байгаа даа. Би докторч асууж асуумаар байна. Та яг ингэж хайж байгаа гол дээр мөсөөрөнгө өргөжсөнийг харсан уу? Манай дөрөвний усан цахилгаан станцын ашиглалтын зохистой байгаа юм. Дөрөвний усан цахилгаан станцыг одоо бага ус цаана явуулж хагаад яг оргил ачаалын үед нэг тавиад тэгээд хэдэн айлын үеийн орсноос болоод энэ асуудал ингээ гараад байгаа. Ийм юм бид нар өөрсдөө ингээ нэг цэцэрхэл асуудал болгоод байхаар чинь мэдгүй усууд мэрэгтийн бус усууд энэ чинь бүх проблем болгож цааш нь дамжуулаад байгаа шүү дээ. Тийм учраас одоо бид нараас иймнүүдаа мэдмээр чинь 315 мегаваттаар гаргах чин чадaltaй Францис төрөнтэйг хүн ярьж байгаа тийм. Тэр бид нар зүгээр энийг зүгээр мөсөө харин яаж үлдэх вэ? Энэ бусад асуу чинь бүр тосгоноор хотоор нүүлгэж байгаа байчих шүү дээ. Тэнд байгаа замаас хадгалж нүүлгээд сэлжүүлээд болж байгаа шүү дээ. Манайх шиг юм өргөө удамтай газар. Тэр ийм юмнуудыг бид нар хоорондоо сайхан ярнөхөөс биш. Ингээд танихгүй мэдхгүй одоо мэрэгжлийн бус усууд бол бочингээ барьчил мөсөнд ороод бочингээ болохгүй юм байна гэдэг ингээд одоо өнөөдөр бид нар эгийн голыг айлгт 30 хэдэн жил яриад барьж чадсангүй шүү дээ. Монголчууд өөрсдөөс болж байгаа шүү дээ бид нар. Орос руу захиа авчиж байна. Одоо энэ чинь гол Орсын нэг Дмитрий хэмлээ тэрнтэй нийлээд одоо ингээд бид нар бүр ашиглаж чадсан. Сая одоо оног болгочихж байна. За энэ эгийн голын хувьд одоо тэр байгаль нуур гэдгээр тэг тавьсан бол онон голын хувьд л арай ингэж чадахгүй баг. Онон гол гэдгээр одоо ашиглах талаар санал тавьдаг. Манай болон дээр зогс одоо энд сууж байгаа. Бид нар мэрэгжлийнхаа ямыг бүгдээрээ ярьж байгаа талцаас нь шийдээд тэгээд ингээд ярихгүй бол одоо сая одоо би хиний тэр орхон ангийн одоо юундаар бид нар судалгаа хийсэн. Одоо ингээд ярьж явах чинь бид нар ийм бол хэрлэн голдоор аль ихт явчих байсан юмыг орхон гэж ойлгож байгаа. Хэрлэн явсангүй орхон ерөөсөө болохгүй, амжихгүй, чадахгүй. Хөрөнгө нь хичнээн сая төгрөгөө. Орхны хүчин чадал ямар вэ? Нөгөө орсууд бас их ашиглахгүй. Ийм юмнууд байгаад байх чинь бид нар өөрөө нэх манайхны одоо нэг цэцэрхүү зангаасууд бид нар өөрөөсөө алаад байгаа. Ингэмээр байна. За баярлалаа.
Thank you, Dr. Chinzer. As it was the last presentation of this session, so I wanted to close the session by applauding to all the presenters in the afternoon session, as well as in the morning session. Thank you. And I would like to ask Dr. Ayurzan to close the international conference officially.
Hello, hello again, everyone. So now it's time to conclude our international session and also to end the Hydroscience and Engineering 2023 International Conference. So today we have discussed a very interesting and various topic from educational remark in hydraulic engineering, hydraulic statics extended by volcanic study and atmospheric waves, as well as basics of open channel flow to morphology of rivers that has to be concerned with the ecological and environmental aspects. We have seen that everything is connected to each other and dependent on each other, as just like surface and groundwater. That is the thing that we keep in our mind in our cooperation. So we have also learned that the UNESCO's action and realized that there are huge amount of research and engineering works to be done to achieve the sustainable development goals, as well as we have a huge opportunity to contribute in that field. Our mission is shared to improve our understanding of water science, link it to engineering, and make a better world. In conclusion, this international conference has provided us with an incredible opportunity to come together and share our knowledge, experiences, and ideas. It has been a forum for collaboration, learning, and growth, and I am certain that the presentations made here will have a lasting impact on our respective fields. I hope that this conference has inspired all of us to continue our work with renewed passion and dedication, and that we can continue to work together towards a brighter, more innovative future. Thank you all for your contributions and participation, and I wish you all the best. Special thanks to our invited speakers for your time and contribution. Thank you.